My dear warriors, in this particular chapter, see, you will see chapter 9 is ray optics, chapter number, 10 is wave optics. They are two different things, but they are related to light. In ray optics, you are mainly concentrating on how the rays of light travel when they encounter a reflecting surface or they encounter a different medium. When they encounter a reflecting surface, that phenomena is called as reflection of light, which you see yourself in the mirror most of the days, correct? Or maybe the rear view mirror of the vehicle. So these are reflection based phenomena. Refraction based phenomena is where the light goes from one medium to the other medium. Example, you wear a lens, or you see through a glass, or you see what is under the water. That is a refraction based phenomena. This is what you study in this particular chapter number 9 of ray optics. You show the rays of light which go, and you see how the path, what is the path that they take, what kind of image is formed, where is it formed, where will you see it, how big is it as it is, or is it been inverted. That is what you are more interested in this chapter. Whereas the next chapter deals with another property of light, which is called as wave property, and wave property is way different. We'll talk about it in the another chapter, which is chapter number 10, right? Okay, that is what has been mentioned in this particular part. Speed of light they have given, etc. Okay, and we have also seen electromagnetic waves, chapter number 8, where light actually travels like an electric field and a magnetic field wave, both of them perpendicular to each other. The direction in which that electromagnetic wave goes, is basically, that path is called as the ray of light. Yes. Yeah. All right. So the path is called as the ray of light, and the bundle of such rays becomes a beam of light. So when I have a torch, it's not one ray, two rays, three rays, four rays. There are many rays bundled, collected together. So then it is called as a beam of light. So like I said, in this chapter, we will consider the phenomena of reflection, refraction, and a little bit of dispersion of light. Okay, and we'll use basic laws of reflection and refraction, and we'll see how the image is being formed in this particular thing. Also, the last part deals with optical instruments. Is that right? Okay, awesome, awesome. Right. Cadets already have made a video on fluids on the JEE channel. You can just search my nurture videos. Please watch that. It is really, really going to be helpful for you. Okay, because it's a very low weightage one. Okay, cool. So now talking about reflection of light, that's section 9.2. Here they basically describe about what is that law of reflection, and this is something which you have studied back in which standard? 10th standard. I hope you remember it still. Yes, when light falls, that is called as incident ray, and the rebounded light is called as reflected ray. The reflecting surface is usually called as the mirror, and the perpendicular drawn to that reflecting surface is called as the normal. There is an angle which is made by the incident ray with the normal, that is called as the angle of incidence, and the angle which is made by the reflected ray with the normal, not with the surface, that is called as the angle of reflection. These two angles, theta, theta, they are equal. That is basically the law of reflection, where the angle of reflection and basically equals the angle of incidence. And they have defined what the meaning of reflection angle is: the angle between the reflected ray and the normal, and the angle between incident ray and the normal is called angle of incidence. Also, the second thing is, this ray, this normal and this reflected ray, all three of them will be in the same plane. It will never be like incident ray came here and reflected somewhere else, or normal is in some weird plane. No, they will all be in the same plane. So the incident ray, the reflected ray, and the normal to the reflecting surface lie in the same plane. That is the second part of the law of reflection. Now, these laws are valid at each and every point on the reflecting surface. This is very important. These laws are valid for each and every point on the reflecting surface, whether plane or whether it is curved. But in this particular NCERT or in this particular syllabus, we restrict ourselves to curved surface. What do I mean by that? See, here whatever reflection has been shown is for a flat surface. Maybe the surface is curved like this, or maybe it is curved like this. So if by chance light enters over here like this, it will, if light enters over here like this, it will reflect back like that. Same thing here also, if it falls like this, it will reflect back like that. If it falls like this, it will reflect back like that. If it falls over here like this, it will reflect back like that. Everywhere you can apply these laws, whether it is a flat surface or whether it is a curved surface. This is flat, this is curved, so it is valid for all shapes, sizes or curvatures. I hope this is absolutely clear. Correct. All right. Now, next thing that they have also told, we will be already discussed geometrical center of a mirror called as the pole. Okay, so here they have redefined what is the meaning of the word, pole, whereas that of the spherical lens is called the optical center. The line joining the pole and the center of curvature of the spherical is known as the principal axis. The principal axis is the line joining the optical center with the focus, as you'll see later. So I'll just revisit this definitions in case you have forgotten it from 10th standard. Obviously, you might have forgotten. So see guys, there are two kinds of mirrors that we usually see in spherical curved mirrors. Normally, if it was a flat mirror, then what would happen if I am standing in front of it? Let's say we take a penguin from Antarctica. If a penguin sees itself, it will see itself erect, it will see itself of the same size, it will see itself exactly at the same distance inside as much as it is standing in the front. That would be for a plane mirror. This is a plane mirror. This is how the light rays are getting reflected, and the image which is formed over here, which kind of an image it is? It is a virtual image. Now you might be wondering, what the hell is this virtual image? If you have forgotten, virtual image is an image which you will be able to see directly. Number one, you can't see it on a screen. Number two, number three, main thing is, you will see that the rays are not going to meet after reflection. Rather, you have to extend it backwards for them to meet. When you have to extend the rays so that they meet and form the image, that's when the images are always virtual, be it mirrors, be it lenses, be it telescopes, be it microscope, anything, doesn't matter. So whenever the rays actually don't meet after reflection, refraction, then the image is not real in nature, it is virtual. That means wherever you extend it and you see them meeting, you will feel, it is virtual, you will feel that something is there over here. Because if these rays, just imagine if I show many rays coming like this, when these rays enter my eye, my brain will start processing and think, oh, these rays are coming from here. So it will automatically create a picture of this penguin in my head. Remember, this picture is not there in reality, it is only there in my head. My brain perceives it as if there is some image over here. That is why it is said to be virtual. So even if you go behind the mirror, you do something, you put something else, nothing will happen, because actually nothing is there. Actually nothing is there. That's why it's called virtual. Whereas in case of a real image, the rays would have merged over there. And if the rays actually physically merge, then if you hold a piece of paper, cardboard or some sheet, you will see the image formed on that particular sheet. Example of a real image, best one, the cinema hall. You would have, I hope you remember the cinema hall. These days people generally sit on Netflix, Prime or YouTube. Well, remember that cinema theater? So there is a projector, and that projector projects light and it falls on a big screen. And those are the points where the rays of light actually physically meet, and you are able to see an image being recreated on that screen. That is a real image and that is obtained on a screen. Is that absolutely clear, everyone? Yep. I'll make a separate strategy video for 150 marks in physics. Don't worry about it. Yep. For now, I hope this is absolutely clear. Now, my dear students, coming back to curved mirrors. So this is a curved mirror, like you can see over here. This is obviously a curved mirror. The curvature is there. Now there are different types of curvature. If it is a flat mirror, that we don't have in syllabus, okay. So this is nothing but a concave mirror because the light rays is reflecting from a surface which looks like a cave where olden people, I mean, long thousands and thousands of years back, people used to stay, or a lion or a tiger stays in a cave. So cave, concave, the light is reflecting from the cave. So concave. And if it is convex, it looks like this. Vex, it bulges. Vex means it bulges. Okay. So this is the bulged out surface. So the light rays are reflecting from that bulged out surface. So that's a convex surface. So it's a convex mirror. So this is how the reflection occurs in the convex or in the concave mirrors, which are also called spherical mirrors because they look like a sphere. I hope you can see that. See, right now it might not look like a sphere, but actually if you keep on extending it, it will complete a sphere. Same thing over here also. It might not look like a sphere. It is actually an arc. If you keep on extending it, it will become a sphere, guys. So that is why, since they are a part of a bigger sphere, that is why they are called spherical mirrors. They are called as spherical mirrors. So as you can see over here, this is a convex mirror. The reflecting surface is over here. This is a concave. The cave is inside. So the reflecting surface is here inside that cave. Next, the mirror will have a center. The center of the mirror is called as the pole, not the center of the sphere. If you divide the mirror into two equal halves, the center of the mirror is called as the pole. Okay, the center of the mirror is also called as the pole. Okay, then if you take that imaginary sphere, the center of the imaginary sphere is called as the center of curvature. The radius of that imaginary sphere is called r, which is the radius of curvature, correct? And the line which goes from the pole to the center of curvature, pole to the center of curvature and pole, that line, okay, which basically symmetrically divides the mirror or the lens, that line is called as the principal axis. That is called as the principal axis. I hope this is clear. Absolutely. Very good. Next, there is also another point called as focus. We'll come to it. Focus is the point where the rays appear to meet or actually meet. So I'll show that as well to you. Don't worry. But I hope these basic definitions are absolutely clear. Pole, optical center, the principal axis, okay, radius of curvature, and all of that. Okay, great. Now, coming to the sign convention part and also to the focal length. I think focal length is there on the next thing. Okay. Now, first coming to the sign convention part. This is very crucial. Let me tell you, the sign convention plays a very important role in not just mirrors, but also in lenses and everywhere. If you make a mistake in the sign, no matter how correctly you do it, you will always generally get a wrong answer. So make sure the signs are correct. It is not as simple as right side is positive, left side is negative. That is very stupid way of looking at sign convention. Wrong. In fact, how it goes is basically everything is measured from the pole. Okay. This is a Cartesian sign convention. You can see Cartesian sign convention. According to this, all the distances are always measured from the pole of the mirror. Always from the pole. That means that point which divides the mirror into two equal parts. Okay. The distances are measured in the same direction as the incident light. This is very important. Measured in the same direction as the incident light are taken as positive, and those measured in the direction opposite to the direction of incident light are taken as negative. So very important. Who is positive and who is negative. Okay. Also, next important thing about height, heights measured upwards, heights measured upwards are basically um, with respect to the normal to the principal axis are taken as positive, and next thing, the heights measured downwards are taken as negative. Okay, so this is basically the sign convention. Now let me help you with that. Imagine there is some object kept over here. The object will emit rays. The rays will go like this. It will fall on the mirror this way. So because it is falling on the mirror this way, so this side of the mirror is positive, the opposite side is negative. Always look at incident light, simple. And whatever is up is positive, whatever is down is always negative. Very easy peasy lemon squeezy. Wherever the incident rays are going, if it is going like this, the mirror will now divide into two spaces, this side and this side, because the light was going this side. So this side will be positive, this side will be negative, as straightforward as that. Okay, okay. Uh, the low weightage chapters will be taken up in the crash course for the JEE. Don't worry. Okay, it's already a part of the crash course. So if you are a part of it, it is already done properly. Number two, in detailed classes of all the chapters is there in VBuddy. My classes, all the chapters, the entire 11th and 12th standard syllabus, I have taught detailed, taking proper time in the VBuddy, which is a part of the crash course. If you have not checked it out, please check it out. Okay. Next, let me show you some examples so that you understand this. Usually the symbols are U is basically object coordinate. V is basically usually the image coordinate. R is basically the coordinate of center of curvature. F is the coordinate of focal point, right? So these are basically the symbols which you will be using in general for mirrors or lenses: focal length, radius of curvature, V, U. So they are the coordinates. Actually, they are not the distances, they are the coordinates. So what do I mean by that? Let's take an example for that. Say this is our mirror like this. This is a convex mirror here. Then let's say this is another convex mirror here. Let's say this is a concave mirror over here. There is another concave mirror over here. Now we all know the principal axis will be basically dividing it in two equal parts, right? Now let's say I place the object. Let's say I place the object and my object is somewhere over here. This is where my object is. This is where my object is. And let's say the image is formed over here. The image is formed over here. Let's say here is where the image is formed. Let's say here I have placed an object. Let's say here I have got an image. Let's say here I have placed an object, and let's say here I've got an image. So these are some random cases that I have chosen, okay, for us to figure out what the sign convention will be. Oops, what the sign convention will be in all the cases. Okay, let's try to figure it out. First of all, always see where the incident light rays are going, where the incident light rays, or from the object they will always start like this, correct? From the object they will always start like this. From the object they will start like this. So I will just show the incident rays so that we have perfect clarity. So from the object they are going to come like this. This is how the incident rays are going to come. The pole is always the origin. The point is always the origin, and wherever the incident rays are going, that side, whichever side they are pointing, that side becomes positive, which means in all these cases, incident light is going this way, so this side is positive. Incident light is going this way, so this side is obviously positive. Okay, incident light is coming this way, so this side is positive. Incident light is coming this way, so this side is positive. Naturally, the other side will become negative. So this is the negative side, even this is the negative side, this is the negative side, and this is the negative side. Is this absolutely clear, my dear students? How we decided which side is positive, which side is negative? Next important thing, my dear warriors, observe carefully. Where is the center of curvature going to be? Well, the center of curvature of this imaginary sphere will be somewhere over here. And let's say the focal length, chumma I'm putting somewhere, okay, is over here. Maybe the center of curvature is over here, and maybe the focal length is over here. Focal point is over here. Maybe, I don't know, chumma I'm putting, maybe the center of curvature is here, maybe the focal point is over here. Maybe the focal point is here, maybe the center of curvature is over here. I've just put some random locations. Okay, now let's figure out what the signs are. Now let's figure out what the exact signs are for object distance, image distance, object distance, image distance, object distance, image distance, object distance, image distance, and next for radius of curvature, focal length, radius of curvature, focal length. Same thing over here, radius of curvature and focal length, radius of curvature and focal length. Okay, let's start with the object distances first. Let's start with the object distances first and image distances. Here the object is on the red line, negative side. So 100% it is negative. Image is on the green side. Yes, it is positive. Here, the object is on that red line. Yes, object coordinate is negative. Image is also on that red line, so negative. Here, the image is on the green one, so V will be positive. Object is on the red one, so it is a negative. Correct. And similarly over here, object distance will be negative because it's on the negative side, and image is on the positive side. So that's how I figured out the sign convention, everyone. Now, talking about the radius of curvature and focal length. What did I tell you? For radius of curvature, check the coordinate of center of curvature. For focal length, coordinate of the focal point. So for R, see where the C is. For R, radius, check where the center of curvature is. It is on the green side, so it is positive. Focal point, it's on the green side, so it is positive. For R, for the radius of curvature, what will you see? You will see where the center is. Center is on the negative side. Focal point also on the negative side. Here, the center of curvature and focal point both are on the negative side. So this is also negative and this is also negative. You can see it's on the red side. Here, focal point, center of curvature is both on the positive side, guys. So this will be positive and this would be also positive. That's how you do it. Everyone clear about this? Everyone clear how to solve these kind of questions? Yep. Awesomeness. Perfecto. Great. So that is basically regarding the sign convention, pole, optical center, principal axis, focal point. Now, what is this focal point also? We'll come to that because I think we had not defined it formally, although you might remember it from your 10th standard. Well, when a parallel beam of light is incident on mirrors, then the rays basically either converge, the reflected rays converge at a point F on the principal axis of a concave mirror, and for a convex mirror, the reflected rays appear to diverge from a point F on its principal axis when a parallel beam of light is incident. So that point is called as F, which is called as the principal focus of that particular mirror, and the distance from the focal point to the principal axis is called as the focal length. Yes, the distance between the focus and the pole is called as the focal length of the mirror. Very, very important. So just going back over here, let's say we take a parallel beam of light. Can I take a parallel beam of light? Little bit difficult, but can I do something? Yeah, maybe over here. See, the rays are the rays are almost parallel if I make it go really far away. If I make it go really far away, and you can see that wherever the rays meet, after or appear to meet, that is very close to the focal point. Same thing for a concave mirror. I know this is not very close, but if I take it really, really far, then the rays approximately try to meet somewhere here. That is where the focal point is going to be. Okay, I unfortunately cannot show parallel beam for some reason over here. Yeah, I can't do that. I'm so sorry. But I'm pretty sure you get the idea. For a concave mirror, it will meet. For a convex mirror, it appears to meet. It will not physically meet. Okay, so that is where the focal point is. From focal point to the pole, that distance is called as the focal length. The symbol for that is basically small f, like I had mentioned before. Now, also very important, this particular thing, which is nothing but f is nothing but r by 2. Very, very important, which means, observe this carefully. If this is your focal length, this focal length is exactly half of the radius of curvature, or f is the midpoint of center of curvature and the pole. Same thing over here. If this much is basically f, then this much is basically r. F is always radius by 2, or f is the midpoint of center and the pole. Very crucial result which you need to remember. R is 2f, f is r by 2, whichever way you want to remember it. If you know radius, you know focal length. If you know focal length, you know the radius. So that is that relationship which has been mentioned over here. Okay. Now, I am interested to figure out where exactly, sir, is the image formed. Now, if you notice over here, I can draw few rays and see where they meet. If the rays actually meet, can you see? The rays are actually meeting. Let's draw it again. See, the rays are meeting. Again, let's see it. The rays actually physically meet here. When they physically meet, the image is real. But let's say if I place the object over here and then see what exactly is happening over here. In this case, the rays don't physically meet. Observe it carefully. After reflection, they are not physically meeting, they are diverging. So I had to extend it behind. So this image is obviously a virtual kind of image. Obviously, it's behind the mirror, so it is virtual. But if the image was in the front of the mirror, then it would be real. So this is the real side, this is the virtual side, because it is behind the mirror. Behind the mirror, nothing can go. So it is the virtual side. In front of the mirror, things can meet. So that is why it is the real side. Correct? Okay. So, sir, you are drawing ray diagram. Yes, I am drawing ray diagram. If you see, one ray is going parallel after reflecting from the mirror, it is passing through the focus. Another ray, I'm showing it, probably going through the focus. And because it is passing through the focus, after reflection, it is becoming parallel. Another ray, I'm showing it incident over here. It is exactly the midpoint. So it will symmetrically reflect back like this. You can see all these rays are meeting here. In fact, if I show many other rays also, they will meet exactly at the same point. Not all the rays get utilized, obviously, because some of the rays will escape that reflection. They will not be a participant in that reflection. Few of the rays will be. But what difference does that make? Does the number of rays matter really? Answer is strictly no, because whether I make the mirror small or whether I make more rays participate in the reflection, the image is still going to be formed at the exact same place. I take a small mirror, I take a medium mirror or a large mirror, the image is still formed at the same place. So what does the extra rays participating in the reflection ensure? You will see that the image becomes brighter because more rays converge, more rays are participating, so the image will be more crisp, clearly visible. It will not be a faint image, it will be a bright image. So the moment I make the mirror small, few rays are participating, so the image might become a fainter image. The location won't change. Is this absolutely clear, my dear warriors? What effect does number of rays have, and what does the effect of size of mirror have on the image location or the image intensity? Bigger mirror has effect of intensity being increased for the image. The actual location of the image won't change. Okay, the actual location of the image won't change because of the size of the mirror. Yes, the size of the mirror has only effects on the brightness or the dimness of that image. Where the image is formed depends on where the object is placed, or how much is the radius of curvature, and all of that. That will decide where the image is being formed. You just need two rays. Actually, you don't need many rays to locate where the image is being formed. This particular method of showing the rays and locating the image, do you have some kind of deja vu from 10th standard? You might have done it and you would have fancied it like anything. Sir, ray optics was my favorite chapter, sir, because you know why? Because we used to draw these rays, we used to show them getting reflected. One is passing through the focus, the one which passes through the focus becomes parallel, and all of that. Or the ray which hits the pole gets symmetrically reflected. In fact, one more ray is there. If you make it pass through the center of curvature, it will come back via the same path. Yeah, that is the speciality of the rays which go through the center of curvature. They will not deviate, they will just retrace back the same path. So you would have done this back in 10th standard, yes or no? Yeah. Rafa Banu, I'll be making a strategy video later on physics, don't worry. Okay, on how to improve your scores from average, below average to 120, 140 zone very soon. Do you remember this? Yes or no? Drawing these ray diagrams. Perfect. Some of you do, some of you don't. Okay, but I hope now you remember what I mean. Okay, clear? Now, usually in your NEET exam, obviously you don't get an answer book where you draw the rays and see where the rays are meeting. So you cannot use the ray tracing method. Like for example, this particular way. We can take any two rays from a point of an object, trace their paths, find the point of intersection, and thus obtain the image of the point due to the reflection of that particular mirror. Like one of the rays could be the ray which is parallel to the principal axis. The reflected ray goes through the focus. The ray passing through the center of curvature of a mirror passes through it, uh, basically retraces the same path, retraces basically the same path. The ray which passes through the focus, the ray which passes through the focus or appearing to pass through the focus, the ray becomes parallel to the principal axis. All these were the rules basically for your ray tracing, which is exactly what this particular simulation is showing. Be it concave mirror or even convex mirror, you can just show some rays and see how they are exactly tracing out, and wherever they appear to meet or actually meet, that is where the actual location of the image is. That was the ray tracing method, correct? But you cannot use this method in the NEET exam unless there is a diagram based question. Usually you will be given distances, how far it is, what is the radius, what is the focal length, where is the image, what is the size of the image. So there is a formula for it directly, and there is a small derivation which is also mentioned in your books. But for a NEET exam, you don't need those derivations. So there is a formula which goes by like this: 1 by V plus 1 by U is 1 by F. 1 by image coordinate plus 1 by object coordinate is 1 by focal points coordinate. This is also called as the mirror equation or mirror formula. What is this called? This is called as the mirror formula or the mirror equation. Directly by substituting values without drawing these rays, you automatically get where the image is. That's the beauty of this formula. Keep in mind, these are sign sensitive equations, meaning if you miss a sign, you will get a wrong answer. So you cannot make a mistake probably. Not just that, if you notice one more thing, this image which is formed sometimes is small, sometimes you might also see it is inverted, sometimes you might see it is erect like this, it's upright. So different possibilities are there. So that has been defined by a term called as how much magnified it is. For example, over here, don't you see the image is magnified? 100%. Now, do you see that the image has been compressed, so it is diminished? But now again, the object is here, this is the image has become enlarged. Similarly, convex mirror, you can see that this is the object, this is the image has been made smaller, the image is diminished in nature. So how big the image is with respect to the object is given by the term called as magnification. How much magnified it is. If I say it's magnified 5 times, that means that means that means whatever the object is, the image is 5 times more than the object. If I say the magnification is half, that means the object is basically 1 unit, this is half unit, this is half of the object's height. That is the meaning of magnification being half. But you will also see magnification comes with a sign. Yes, magnification does come with a sign, positive and negative. Sometimes it can be +5 or -5. It can be plus half or minus half. What do I mean by that? If it is negative, that means the image has been inverted with respect to the object. And if the magnification is positive, that means the image is upright, erect with respect to the object. That's the meaning of the sign which comes in the magnification. So I'll put it over here. If 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 let's say, for example, magnification, the symbol for that is M, is positive, that means it is upright, it is basically upright or basically erect. If the magnification is basically negative, it is basically inverted in nature. Next important thing, if the magnitude of the magnification is more than 1, then it has been enlarged, it has been made bigger. If by chance the magnitude of the magnification is less than 1, then the image has been made diminished, it is smaller than the object. And lastly, if by chance the magnitude of the magnification is 1, then by coincidence it will be of the same size. For example, right over here, say I put the object here, can you see the image is of the same size? Yes, the image is of the same size. So the magnification's magnitude is 1, but the sign of it is negative. So technically M will be -1. M will be how much? -1. Everybody agrees with this? Why is it negative? Because it has been inverted. Why is it 1? Because size is the same. So the size is decided by the magnitude, and the sign decides whether it is upright or whether it has been inverted. Clear, my dear warriors? So the formula for the magnification, my dear students, is given over here. It is V by U with a negative sign. V by U with a negative sign gives you the magnification, which is image height by the object height, image size by the object size. That gives you magnification. How many times is the image magnified with respect to the object? Negative of image coordinate by object coordinate. This is also sign sensitive, meaning numerator denominator can be positive or negative. Accordingly, the sign of M can change. Accordingly, the sign of M can change. Don't worry, we'll be doing questions on this now. All right. So probably here is the one of the first questions coming up on your screen. This is there in your in-text NCERT. Example 9.1. Suppose that the lower half of the concave mirror reflecting surface is covered with some non-reflective material. What effect will it have on the image? Think about it. Imagine there is a mirror like this, and you had an object over here. This was your object. So usually what would happen? The rays from the object would go like this, will go, like this, like this, and then reflect also, correct? They will also reflect, maybe like this, maybe like this, maybe like this, maybe like this, maybe like this. They're reflecting, and they're maybe making a image over here. Now, what will happen if somebody removes this? Basically, they cover it with a opaque material. Then you will have fewer rays getting reflected. Only these rays will get reflected. These rays won't get reflected. Only these rays will get reflected, which are on the top. So because of which, what will happen? The image will be formed still at the same place, just that the image will be slightly dimmer. Yes, so the image will be of less intensity, but the image location will still remain intact. Correct? I think I just showed it to you sometime back over here only when I showed these rays, and I told you doesn't matter what the size of the mirror is, the location is the same, the intensity of the image will definitely change. Cool. Give me a thumbs up. Can we go ahead to the next question coming up on your screen, my dear students? All right. Here it comes. There is a mobile phone, okay, lies along the principal axis. Can you see there is a mobile phone right over here? In case you are not able to see, this is it. Okay, this is a mobile phone. Nowadays, we don't get the antennas separately. 20 years back, 15 years back, there were mobile phones with antennas popping out of it. So nowadays, we don't have it. Okay, show by suitable diagram the formation of its image. Explain why the magnification is not uniform. Will the distortion of the image depend on the location of the phone with respect to the mirror? Okay. Now, basically, this was the object, and the image is basically like this somewhat. The image is basically somewhat like this. The question is, see, the mobile phone was almost rectangular. Why the image has become something like a trapezium? I think the idea you will get it right from here. Just check this out. Okay. Just imagine, just imagine, this is where the first part or one side of the mobile phone is. Let's say this is the mobile phone. Okay, this is the mobile phone. Where is the image formed? It is formed right over here. The image is formed right over here. Now, what I will do, I'll just shift the object over here. That means I'm trying to find where the reflection of this part will be. The reflection of this part is here, and it is much smaller. If I shift this arrow mark here, I'm trying to find the reflection of this part. The image is over here, even smaller. If I take it over here, the ray, then you can see the reflection is here. It is even smaller. So right from the beginning till the end, you can see every place on that big, mobile phone, whenever I try to find the reflection, whenever I try to find where the image is, the images are not of the same size, because every object distance will give a different image distance, different magnification, different size. So that's why, although the object height might be the same, the image heights will not be the same at different places. Is that clear? So instead of placing the mobile phone over here, had I placed the mobile phone over here, then the distortion will be even more different. Like if I slowly change the object locations, you can see the image is formed at different place. If I place the mobile phone over here, then maybe it will be formed at a very different place. It will be, the images are formed here, here, and here. You can see if I place the object at different places. So where you place it matters. Also, the magnification is different for different object distances. So that is the true answer to this. Okay, so I can just say that for this particular object, probably this could be the image. Similarly, for this particular object, maybe this is the image. That is the reason for that. Different object distances, different image distances, different magnifications. Next question on your screen now. 9.3. An object is placed at 10 centimeters, 5 centimeters from a concave mirror, radius 15, find the position, nature, magnification of the image in each case. So, okay, first things first, it's a concave mirror. Let me remind you of that. If it is a concave mirror, if it is a concave mirror, the center of curvature will be here. Focal point is the midpoint of the center as well as the pole. Okay, the object will be placed somewhere on this side in front of the mirror. So that means this will be the positive side, and obviously this will be the negative side, because the object will be placed somewhere over here. The rays from the object will come like this. The rays from the object will come probably like this. Okay, this is from the object. Okay, so that's why this side is positive, this side is negative. This sign convention should be absolutely clear. Now, can you see the radius of curvature will technically not be 15, it will be negative 15. So technically the radius of curvature will be negative 15 centimeters. Everybody with me on this? Okay, what about F? F is nothing but R by 2. So whatever 15 is there, divide by 2. So minus 7.5 centimeters. So R by 2. So that's why negative 7.5 centimeters. Correct. Oh, yes. Definitely. I'll have water after some time. Thank you so much, Krishna, for reminding me. Okay. Now, once I know F, let's do it for part 1 and then let's do it for part 2. So part 1, object is over here. So object distance will be negative 10. Object distance will be negative 10. So when I use 1 by V plus 1 by U is equal to 1 by F, U will be negative 10. F will be already mentioned over here, negative 15 by 2. You can put it negative 15 by 2 or something like this, or negative 7.5. So that would be my equation which I will be solving. How to solve such equations? Some of you usually face some difficulty because things are below, not on the top. So this will be nothing but 1 by V is equal to, take it on that side, 1 by 10 minus 2 by 15. F15 and 10, the LCM is 30. 10 goes with 33 times, 15 goes with 32 times, so 2 2s are 4, so it will be negative 1 by 30. So therefore, the image distance will be negative 30 centimeters. Now, the moment I get the image distance, have we got negative 30? Yes. Negative 30, it clearly means the image will be formed this side in front of the mirror. That means the rays will reflect and they will meet physically. So definitely the image is going to be real in nature. It is going to be real in nature. Everyone? Great. What about the magnification? Magnification is negative V by U. So V is negative 30, U is basically negative 10, negative, 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 one negative remains and negative 3 will be the answer. This negative says that it is inverted. It is definitely inverted. But this number 3 says it has been enlarged. The size of the image is going to be big. Yes. So to show you practically how it would be, most likely it will be something like this. The object will be here. The image will be here. The object is at 10 centimeters. Check this out. Object is at 10 centimeters. Image is at 30 centimeters. Image is formed at 30 centimeters. The image has been inverted, but it is triple the size of the object. So this is approximate ray diagram of this particular problem which we have just solved. Is that clear? Yep. Now, if you look at the second part of the problem, when it is 5 centimeters, so you will take U as basically minus 5. Why minus 5? Because object will be again in front of the mirror, and then use similar logic, 1 by V plus 1 by U, U is negative 5, is equal to 1 by F, F is nothing but your negative 15 by 2, negative 15 by 2. Solve this again just like you did it over here by taking LCM. The V value comes out as 15 centimeters. Now, because you got it as positive 15, it clearly means the image is formed on this side behind the mirror, means the image is going to be virtual in nature. Talking about the magnification, it will be negative V by U. V is 15 and U is basically minus 5. Minus minus cancels, it will become 3 times. So this means it is nothing but erect because it is positive, but it is enlarged. So most likely the possible diagram for that would be something like this. It will be like this. The object is 5 centimeters in front of the mirror. Object is 5 centimeters in front of the mirror. Image is 15 centimeters. 15 centimeters behind the mirror. It is virtual. You can see it is erect and it has been magnified. It has been magnified how much? 3 times. It has been enlarged 3 times. Clear? So this is how it is. So I hope you are getting a feel of the NCERT problems as we are solving. I'm demonstrating over here how and what this actually means in reality. So we are actually feeling physics here. We are not just solving the problems blindly. We are getting a feel of what this problem might actually look like in reality. Great. Cool. So if you don't like arrow marks, you can always use penguins. Penguins are cute and penguins are rare and penguins are fun. Okay, so there we go. Okay, awesome. But this penguin is huge. It's the head is getting chopped off. Okay, but now it's not getting chopped off. Perfect. Cool. So moving on to the next question coming up on your screen, and here it is. Suppose while sitting in a parked car, you notice a jogger approaching towards you in the side view mirror. So you're in a car, side view mirror is there, and the side view mirror is usually a convex mirror. Radius of curvature is 2 meter. The jogger is running at 5 meters per second. How fast the image of the plane will be? Okay. How fast the image of the jogger appearing to move when the jogger is at 39, 29, 19 and 9 meters away. So basically at different places they have asked you what might be the approximate speed of it. Okay. So here is the logic behind this. Imagine this is our convex mirror. This is our convex mirror. The object will be here, so the rays will be going like this. That means this side will be positive and this side, oops, and this side will be obviously negative side. Okay, so we have a jogger who is coming from here. So maybe the object is over here and the jogger is, how many meters away? The jogger is appearing to move 39 meters. Okay, the jogger approaching towards you. Okay, so we are like this. This is the mirror. The jogger is coming like this towards us. So after some time, that same object might come over here. That same object might come over here. Maybe earlier, this particular distance, could have been maybe 9 meter. So technically object distance is negative 39 meters, So, after 1 second, because the jogger is running at a speed of 5 meters per second, after 1 second from 39, 39 minus 5 will be 34. So the jogger will be at a distance of how much? 34 meters. This is going to be object distance, which is negative 34 meters. So this is basically in 1 second. This is in 1 second. This is what has happened. From 39 meters, you have gone to 34 meters because the jogger speed is given to be 5 meters per second. Is this clear? Wave optics after ray optics. Probably it will take few days. Sometime next week or next to next week. Okay, cool. Till this point? Perfect. Now, my dear students, observe this very, very carefully. Because the object has moved, the image will also move. And that is what the question is, what speed will the jogger appear to me at? So what will you do? For this particular object distance, try to find where the image is. Use this formula, 1 by V plus 1 by U is negative 39, is equal to 1 by F, focal length not given. So what I will do, this is where the focal point will be, this is where the center of curvature will be. radius it is positive 2 meters, f is r by 2, so it will be basically 1 meter. Okay, so this is just going to be 1 over here. From this, you will get what the image distance is. You will get basically what the image distance is, and I think they have found it out to be 39 by 40. 39 by 40 meters. Do the same thing for this as an object and see where the image will be. By using the mirror formula again, 1 by V plus 1 by U will be negative 34 is 1 by F. What is the focal length? It is again plus 1 meter. Okay, solving this, you will get the new image distance, and I think the answer that they have got is 34 by 35. 34 by 35 meters. So can you see both of them are positive? 39 by 40, 34 by 35. So what it means is that the image has shifted. So the shift in the image, my dear warriors, so the shift in the image will be just V1 minus V2. Whatever is bigger, you take first, and what answer you get over here is 1 by 280. 1 by 280 of a meter. And all of this is happening in 1 second. Very, very important. So the person is moving at 5 meters per second, the jogger, but in the mirror, the person is hardly moving 1 by 280 meters in 1 second. Isn't the speed much slower in the mirror as compared to the one in an actual? Isn't the speed in the mirror much slower than the actual speed of the jogger or the object out there? This is why you will see on the rear view mirror of vehicles, they write that the objects in the mirror might be closer than they appear, because you might see them moving slowly, you might see them small, you might feel that, okay, they're small, they might be far, but actually they are much closer than what they might appear or feel in that particular mirror. That's the reason for it. Okay, then you can do the same exercise for the other distances and all of that. So that is what has been done in this particular problem. Is that clear, everyone? Okay, beautiful question. Just to make you visualize this, imagine I'm sitting in the car. This is my side view mirror. I see suddenly from Antarctica, one penguin starts running towards me. Penguin is jogging and coming towards me. What will Shreyas Sir see? Shreyas Sir will see the image of the penguin inside the car's mirror like this. And you will see that earlier the penguin was here, now it is moving here, it is moving here, it is moving here. See, this penguin, Pavam penguin from Antarctica is running so much, but the image is hardly moving. So that is why it creates a apparent feeling that, you know, the objects behind are slower, the objects behind might be very far away, but actually see, this penguin is running so fast, but this image is hardly moving anything over here. So it might make me feel the penguin might not be fast, but actually it is very fast. Got it? Did you visualize it now? I'm pretty sure you would never have seen this demonstration before this. I know you have seen it practically in your rear view mirror, but ray diagram wise, this is what I mean, by the instructions which are mentioned on the rear view mirror. Objects in the mirror are closer than they appear. In fact, I feel there should be one more notification which should be written on your wall. Yes, just like in the side view mirror, they write objects in the mirror are closer than they appear. On your wall, what should be written is, yeah, the exam, or basically the NEET exam on paper may seem farther than it actually is. Isn't it? You feel that, oh, NEET exams are 1 year is there, NEET exams are 2 years are there. That's what you thought in 11th standard, right? Then 12th standard, oh, 1 year is there. Then maybe drop year, oh, NEET exam came and went, okay, next year I'm going to work hard. drop year. Okay, fine, sir. NEET is 1 year away. Then suddenly it becomes 200 days, 180 days. And then you are like, okay, sir, NEET is 5 months away. Okay, I can manage. But actually, it is not 5 months. It's less than 5 months because you have to spare some time for revision, mock tests, strengthening your weak points. And, some days might be low. Sometimes you might not feel like studying. Some days you might just fall sick. Who knows? All those things you have to take into account, and you need to keep some buffer time. That's why you have to complete the syllabus way in advance, right? And don't worry, there is something really cool which we are going to get for you. And yeah, it's going to come up on the channel very soon on 28th of November, because most of RNA done, DNA batch almost coming to an end, and the DNA students too are very eager, sir, what's next? And yeah, the plan for them too is coming up. And all the things which you might be looking forward to might be answered very soon. So stay tuned on the channel is what I would say. Right, correct. Let's move to the next part, and that is a refraction. Okay, beautiful. Refraction is the phenomena where the light goes from one medium to the other medium and changes its path, changes its speed, changes its wavelength, but not its color. I mean, if blue color entered water and suddenly blue became green, that would be weird. I mean, imagine a fish which you take out from the water, maybe it is green in color, but you dip it inside the water, it looks yellow. You're like, what the hell? Green became yellow. Or you are swimming underwater, you are brown or white or wheatish in color, suddenly you start appearing orange. You're like, oh, Shreyas sir, underwater you look orange, sir. No, that doesn't happen. So frequency of the color, frequency of the light does not change when the medium changes, but it's the speed, the path, the direction changes, even the wavelength changes. So this phenomena of bending, changing the path of the light with the speed is called as refraction. Okay, so yeah, so I think I can mark few things. A beam of light enters another transparent medium. A part of the light gets reflected. Part of the light gets reflected into the first medium, while the rest enters the other. Okay. This phenomena is called the refraction of light. Snell's experimentally obtained the following laws. Okay, and also mentioned over here is the incident angle, which is less than 90 degrees and more than 0 degrees. So what are the two laws which Snell obtained based on that? See, there is one medium here, there is another medium over here. You can see there is a normal drawn over here. This is the ray which is falling. It changes the direction. It was supposed to go here, but it has deviated very clearly, and the path has been changed because of refraction. So this angle is called angle of incidence, but not all the light will go here. Some of it will definitely get reflected by laws of reflection. Some of it will get transmitted, which is then called as the refracted ray. So the angle made by the refracted ray with the normal is called as angle of refraction, not reflection, refraction. That is the angle of refraction. So the first law as per Snell is that the incident ray, the refracted ray, and the normal are in the same plane. Makes sense. Everything has to be in the same plane. It would be very weird if light is coming like this and the light after entering water is going somewhere else only, and normal is somewhere else. It doesn't make sense. So it has to be in the same plane. Okay, next important thing is if you measure the sine ratio, trigonometry, sine, cos, tan, cot, sec, cosec, that one, sine of the angle of incidence and the sine of the angle of refraction, and you keep on introducing different angles of incidence, it will keep on getting refracted at different angles. Every time the ratio of sine of incidence and sine of refraction is a constant value, which is called as the relative refractive index. This is called as the refractive index of the second medium with respect to the first medium. Some books use the symbol n, some books also use the symbol mu, and you can write it like this, mu 1 2. So when I put like this, it is the same as n to 1, very confusing. When I write 1 mu 2, it means light has gone from medium 1 to medium 2. Light has gone from medium number 1 to medium number 2. But while saying it, you will say refractive index of 2 with respect to 1. Got it? Just like when you have velocity 2, 1. What do you mean by it? Velocity of 2 with respect to 1. Same way over here also, this is a refractive index of 2, refractive index of 2 with respect to 1. That is how it is pronounced, but while writing, you will write 1 mu 2 or n 2 1. So it's up to you which convention you want to use. Everything is the same thing, depends from book to book, and your NEET exam NTA paper can have any of the symbols. It doesn't really matter. Okay, now this constant that is there, it depends on what is the medium here and here. So if I, instead of water, I use glass, it will be very different constant. If I use diamond, it will be very different. If I use glycerin, it is different. If I use some plastic transparent type, it is very different. So this ratio which I got is constant. That constant, it depends. That constant basically depends. It's a characteristic of the pair of the media. And I say pair means both. Not just this, it also depends on what is there on medium one side. If instead of here air, if you use some other gas, maybe some smoke, it might be different. If it is vacuum, it might be different. If it is water, it might be different. So both of them, both means pair. So it depends on the pair of the media. And you will see it is independent of the angle of incidence and also depends on the wavelength. That will come to it later on in the concept of dispersion. Okay, so having said this, let me also tell you the different things over here. There are few formulas. I will make you understand this. Yeah, like this. Okay. Usually the refractive index to 1 means light went from 1 to 2. That is how it went. Light went from medium 1 to 2, which is said as refractive index of 2 with respect to 1. This is relative refractive index, but it can be also written down as mu 2 by mu 1, where these are absolute refractive indices of the medium. When I say absolute refractive indices of the mediums, meaning it is with respect to vacuum. It is with respect to vacuum. Usually light might enter from air. Air is almost as good as vacuum only. So you can say anything measured with air or vacuum approximately is absolute refractive index. Usually light will come from some bulb in our surroundings, atmosphere. So we measure everything with respect to air or vacuum. So that's why we have this term absolute refractive index. Light entered from air to glass, light entered from our surrounding to diamond, light entered from something to a transparent, some maybe a plasticky sheet or some translucent medium, amber glass, thing like that. So that's why we have this term absolute refractive index, which is mu 2 by mu 1 is 1 mu 2. 2 goes on the top, this 1 goes over here below. Keep that in mind. And you can therefore also say, if 1 mu 2 is mu 2 by mu 1, 2 mu 1 will be mu 1 by mu 2, which is exactly opposite of this. So I can always put a reciprocal over here, and I can put 2 over here and 1 over here, which means if light went from 2 to 1 instead of 1 to 2, then the refractive index relatively will be reciprocal of the previous one. Kind of makes sense. If you reverse the direction of light, obviously the refractive index will be a reciprocal. That is what has been even mentioned over here. N12 is N21. Okay, don't get confused. Right? Clear? Also, as per Snell's law, what did we write over here? Sin I by sin R, right? So this is also equal to sin of I by sin of R. Not just that, let me also tell you, it is speed of light. It is also speed of light in the first medium upon speed of light in the second medium. These are basically speeds of light in different medium, different medium. But we also know speed of light, speed of light is frequency into wavelength. Frequency into wavelength, but frequency won't change. So f into lambda, f will be the same. Frequency is going to be the same, but obviously wavelength changes. Wavelength definitely will change. Keep that in mind. Wavelength will change. So this is the main formula which you should know. Main formula which you should definitely know. Now think like this. If you have things like this, okay, this is an interface. Let me also show a normal. Let's say there is a light ray which goes from this medium and bends like this. Second case goes like this and goes like that. Obviously, this would be the angle of incidence, this would be the angle of refraction, this would be the angle of incidence, this would be the angle of refraction. Obviously, this was medium number 1, this was medium number 2. Light is going from 1 to 2. Sine of I by sine of R is 1 mu 2. Speed of light in medium 1 by speed of light in medium 2. So this relationship holds true. What is different in both of them is that here the refracted angle is less than I. So R, the refracted angle, is definitely less than I. Here the refracted angle is more than I. So here I can say it bends towards the normal. Bends towards the normal. Whereas over here it bends away from the normal. It bends away from the normal, as you can see over here. It bends away from the normal. In such cases, when it bends towards the normal, I would say this is relatively a denser medium. This is relatively a denser medium, and this is relatively a rarer medium. When it bends away from the normal, then relatively this is a denser medium, and when it bends away, then this is said to be a relatively rarer medium. Now, when I say rare and dense, don't think density in terms of kg per meter cube. The density which I am referring to over here, which density is it? It is optical density, which is way different than, your normal kg per meter cube density. That is mass density. This is optical density. There is no unit. It is just a qualitative term. So whenever you bend towards, it's denser optically. Whenever you bend away, it is relatively less dense or rarer. So that is the reason why you will see this note. Optical density should not be confused. That's why they have mentioned this. Optical density should not be confused with mass density, which is mass per unit volume. It is possible that something might actually have more density, but optically it is less dense, and vice versa. And for that they have given an example also, which I feel it's better to remember. For example, turpentine and water. The density of turpentine is less than that of water. If you measure in kg per meter cube, for water it is 1000 kg per meter cube. Turpentine it is slightly less. But optically it is more dense, meaning if light enters turpentine, it will bend towards the normal. Although the density of turpentine physically kg per meter cube is less, because the density which we are referring to in ray optics is optical density and not the kg per meter cube density. Clear? Also keep in mind, when this thing happens, when it enters a denser medium, the speed becomes less. The speed becomes less. Yes, the less, it will have less speed over here. Not just that, uh, because it is entering a denser medium, the wavelength is also going to be less. Because if speed reduces, even the wavelength will reduce. Whereas over here, you will see the speed will be more, the speed will be more, and even the wavelength is going to increase. Because it is entering a rarer medium, it will fasten up and the wavelength will also elongate. That is what will happen. If you ask me the refractive index relatively, over here, the relative refractive index, because it is going to a denser medium, it will be more than 1. When it goes to a rarer medium, the relative refractive index will be less than 1. So whenever refractive indices are more than 1, you are entering into a denser medium. If it is 0.8, 0.7, 0.6, you are going to a rarer medium. Correct. I'll just drink some water, just write it down. Thank you, Krishna Madhumati. Thank you so much. Great. So we have understood now how refraction works over here. Now there is one more thing over here which you should definitely know, and this can be useful in some cases. Say for example, um, if you have something like this, refractive index of, let's say you have to find, of A with respect to B, what you can do is, yes, you can write it as mu B by mu A. That is one way. You can also write it like this, mu, mu. You can multiply as many terms as you want. I'll just put it some examples over here. I can put even 4 terms, doesn't really matter. Just see who is the first term. First term is A, right? So start with A. Start with A. Last alphabet is B. So put B towards the end of a chain. And all these refractive indices are basically multiplied, let me tell you. Now in between, you can form a chain. Say for example, you can just say this is C. So it will be C over here. Okay, A to C, C to B. You have to jump like a chain from A to C, then from C to, let's say, D, from D to, let's say, E, and from E back to B. So you can form a chain, and this can be very helpful whenever you want to convert from one thing to the other. Okay, you know refractive index of something with respect to something, you have to find it with respect to something else. So this chain rule you can definitely use. So this is something like your chain rule. You can make this chain as long as you want. Okay, so that also I think has been mentioned somewhere over here. Yeah, this one, this is that chain rule. This is basically that chain rule in that NCERT paragraph. They have not mentioned it, okay, but still telling you. All right, all right. And here also all these things are mentioned, which we have talked about, rarer, denser, and all of it, right over here. Rarer, denser, what happens to the speed, wavelength, everything has been mentioned over here in a very small way, but I have obviously explained it to you very neatly. Okay, let's see the example of refraction, of course. But for that, let me go back. Okay, refraction. Where the hell is refraction? Right over here. Bending of light. Cool. Let's see. Okay, there we go. As you can see, I have a torch. I can turn on that torch right over here. If you want, I can also measure the angle and all of it. I think that tools also they have mentioned if you want to measure the angle properly, but it's okay. I don't want to measure it. Just keep it here. You can see I can select different materials: air, water, glass, some unknown material A and B, and you can choose your own material. Right now it's air. I can choose this side also: air, water, glass, some mystery material, or my own material. Right now it's water. Let's turn on the light. You can see the light falls here, gets reflected, some of it, and the rest of it gets refracted. It might not look very apparent to you that the light has got bent, but actually the light has got bent. Let me show it to you like this. Now you can see very easily. See, this is the angle of incidence. This is angle of refraction. It is obviously less than the angle of incidence, so it has bent towards the normal. So definitely this is a denser medium. This is a rarer medium. Now just see what will happen. Instead of this being rare and this being dense, I flip it. Maybe I make this also water. If I make this also water, it is in water only, so it will not get refracted, of course. But if I make this as air, can you see it is bending away from the normal? So now this is a rarer medium, this is a denser medium. Yeah, some of it is getting reflected, the rest of it is getting refracted over here. I can change back to the same medium. Now it is getting again closer towards the normal. If I change this medium to, let's say, glass, you can see the angle of refraction has changed. In fact, let me choose it as custom. See this, if it is air, it doesn't bend. As I increase the refractive index, the light bends more and more towards the normal. And it is more apparent if I keep a large angle of incidence. Then you can see as I increase the refractive index, it bends more and more towards the normal, right? Very, very clear. Same thing I can do opposite also. Let's say you are in that custom material and you are coming out in air. If I make this denser, you will see, if I make this denser, you will see it will bend more and more away from the normal if I make it more dense, right? That is what is happening. Awesome, awesome. Now there is a problem. I'll tell you what the problem is. And we are going to come to that as well. I think it is on the next slide. Yeah. Oh, actually, it will come later on. First, they have explained about that phenomena of apparent depth and apparent height. So you might have seen that if you enter a swimming pool, uh, if you look at the depth of the pool, it feels that it is not so deep, or the lake, you might feel it is not so deep. Or suddenly when you put your feet inside water, you feel that your feet has got compressed. It's much smaller than what it is actually. So this apparent notion is called as apparent depth and apparent height concept. So if you are in a rare medium, seeing inside a denser medium, it appears closer. So keep in mind. So if you are in a rare medium and you look at an object in the denser medium, so the observer is in the rare medium. The observer is in the rare medium. Then what happens is the denser medium's object comes closer. So this is where the object is, but the image will come over here. It will appear to be closer than what it actually is. If it is very deep, this is the actual depth h naught. This is the actual depth h naught. This then becomes h1 or h prime, which becomes the apparent depth. And this apparent depth, this particular apparent depth happens to be the actual depth by the refractive index, by the refractive index of the dense medium with respect to the rare medium. So that is how it is. H prime is actual depth, whatever the actual depth is, you divide it with a number more than 1. Refractive index of glass, etc., 1.5, 1.3. So you will see the apparent depth will be smaller. This one was the actual depth. Got it? The reverse also holds true, by the way. The reverse also holds true, meaning, say for example, if there was an observer inside the denser medium and that person happens to see some object right over here, so technically this would be the actual This would be the actual height, but the image will be formed over here. The image will be formed over here. This will be the apparent height, and this apparent height will be actual height. Instead of dividing, now you will multiply refractive index of the denser medium with respect to rarer medium. So this is what happens when you are in the reverse mode. You are in the denser medium and seeing an object in the rare medium. So imagine the dynamics in nature and how beautiful nature is. A fish which is being hunted by a bird from above the surface. When the bird sees the fish appears to be closer. The bird thinks, oh, the fish is here, but when it dives, I mean, it's a complete flop show for the bird, because the actual fish is over here, right? The bird gets fooled into thinking the fish is not here, but rather here. So it feels apparently closer. The reverse, the reverse of this, just think about it. The fish peacefully swimming in the water feels the bird is really far away. But as it comes close, then it realizes actually it was not far. That was the image. The bird was actually over here. So both in a way get fooled into thinking, one is closer or one is farther. And that's how the dynamics plays. But by experience, through evolution, both of them know that if the bird is seeing the fish, it's not actually there. It's much deeper. So it actually dives more. And the fish genetically, through experience and thanks to the forefathers and evolution, it knows that if the bird is over here, it's not actually there, it's much closer, so it will go much deeper inside the water. So it's now a battle of who is going to be the smarter one and stronger one. So survival of the fittest and the smartest, actually. Okay, so that's what it is, which has been mentioned over here, the concept of apparent depth right over here. Okay, something which you should be aware of. Just block the formulas just in case you've not done that yet. Okay, this is when you see inside the denser medium. This is when you see in the rarer medium. Observers are at two different places. Okay, now the next limitation comes of refraction, and this is also very interesting. Abhishek, I'll be coming to the Karnataka channel. Just give me some time. Just give me 1 or 2 days. Lot of things are there. I'm trying to wind up as much syllabus as possible on all the channels and coming there. Don't worry. Luckily, Gopika ma'am, Diksha ma'am, everyone, and Baswa sir, everyone are taking classes. So I'm held up at many places. I just don't have one channel. I have 4 channels to take care of, plus the crash courses which are going on. Okay. Let's go to the next point, which is basically the total internal reflection. Now, my dear warriors, what is this phenomena? I'll explain this to you very simply and beautifully. See, if the light goes from a rare to a dense medium, like over here, there is no issue at all. No matter what you choose as the angle of incidence, the light will always go into the next medium. Light is always going into the next medium, no matter what you choose as the angle of incidence. So always the light gets refracted into the other medium. But the problem happens in the exact reverse way. Just imagine if this is air and this is dense. Okay, this is something like, say, over here. Now, okay, for small angles of incidence, it is fine. For small angles of incidence, it is fine. It is getting refracted. But check over here. After this point, I can see the refraction does not occur. Only reflection occurs. You can see it is behaving like a mirror. So, two different mediums can behave like a mirror if you choose a large enough incident angle and if the refractive indices are really different for those two mediums. So, as you can see, if I choose a normal medium with a very small refractive index, the angle till which refraction occurs, okay, somewhere over here, yeah, that's it. Till here about refraction occurs, after this refraction is not occurring. So this is the critical angle for that pair of media. It's the angle till which refraction occurs, beyond which refraction doesn't occur. That is called as the critical angle, and it only happens when light goes from dense to rare and never from rare to dense. Keep that in mind. If I choose a more dense medium from which light is entering, then the critical angle will be even more less. Check this out. Now you can see the critical angle is way less. So it started reflecting right over here. See, that's it. After this, there is no more refraction, only light is getting reflected. But if I choose a normal other kind of medium, then the light will definitely refract. I will need a much higher angle of critical incidence so that it only gets internally reflected. So when this happens, light is getting reflected internally in the denser medium. This phenomena is called total internal reflection, TIR, total internal reflection, which happens after the critical incidence, Is this absolutely clear, everyone? So I can definitely then say over here, let's say like this is the medium interface. Let's say this is the normal. Let's say this is dense. Let's say this is rare. And let's say we're talking about the critical angle. So light goes like this, and that's it. It is just going like that. After this, you choose any other angle. Let's say like this, it will just get internally reflected. So there is definitely total internal reflection. But before this, if you choose any other angle, the light used to come out also. Not just that, it also used to get reflected. So both were happening before that angle. So definitely this particular angle is our critical angle of incidence, and when that happens, the angle of refraction is 90°. So sine of IC by sine of 90 will be, light is going from dense to rare, so refractive index of rare medium with respect to dense medium. Sine of 90 degrees is basically 1, and usually you never get refractive index of rare medium with respect to dense. Usually it is the other way around, like refractive index of glass with respect to air, water with respect to air, never air with respect to water. So whenever we have to reshuffle these variables over here, it is a reciprocal, and that is something which I gave it to you over here itself, right? 1 mu 2 is 1 by 2 mu 1. So you can just flip it around, and it will just become 1 by mu of the dense medium with respect to rare medium. So basically sine of that critical angle is 1 by refractive index of that particular dense medium. That's it. That's the formula, guys, which you should definitely know. Okay, I hope this is absolutely clear. Cool. Now, different refractive indices, everything are given on the next table, and their critical angles. Notice how for water the refractive index is 1.33, for some glass it is 1.52, for some different kind of glass it is 1.62, for diamond it is 2.42. As you can see down the chart, the refractive index keeps on increasing. Which means, going back over here, this value is increasing. That means the denominator is increasing. So the ratio will decrease, which means the value of the critical angle on the left hand side should also decrease. So that is exactly what you see. Although the refractive index increases, the critical angle decreases from 48 to 41 to 37 to 24, because it's reciprocal. Can you see that? Reciprocal. Yeah. If mu increases, I will decrease. So a more dense medium like diamond or flint glass will have a smaller critical angle. So the probability, the chance that the light might escape it is less. Very critical, guys. Observe this very interesting thing. If something has higher refractive index, then there is a greater chance that light may not escape it. Like see this, if this is water, till here you can see the critical angle exists. If it is less dense, it is still refracting. If it is more dense, it's already internally reflected. So a dense medium will have a smaller angle of critical incidence, so it will reflect very easily. There are so many options for getting it reflected internally, but when the medium is not so dense, the options are not so many. Only few options are there for which it will get internally reflected. Other than that, it will refract itself. So that is the reason why once light enters the diamond, it will not easily come out of the diamond. It will get reflected many times, and once multiple reflections occur, that's the reason why the diamond will shine eventually when the light enters your eye. Got it? Why the diamond shines is because of multiple internal reflections, right? Total internal reflections. And there are many applications also based out of it. Prisms used to deflect light by total internal reflection, such that the light will not uh, exit out. So this prism is particularly very interesting. This prism has no mirror, but it is acting like a mirror because the refractive index of the prism is very high. Observe this carefully. Prism is basically a cut piece of a glass, looks like a triangle. Prism shape everybody knows. So if the light is entering, once it has entered the medium of the prism, it's in the denser medium. As you can see, this is the angle of incidence. But if the refractive index is high enough, then it will not be able to exit into the air. Rather, it will get internally reflected. So it is getting totally internally reflected. So the surface of the prism is as if acting like a mirror, as if acting like a mirror. So the prism is used like a mirror, and this is also used in many cameras, telescopes, microscopes to change the direction of the light. In fact, the direction of the light can be even reversed using a prism, something like this. Check this out, light enters inside the prism. This is the dense medium. As you can see, if you draw normal, this is the angle of incidence. If the refractive index is high enough, then the critical angle criteria is met. Then it will not enter the air medium. Rather, it will get internally reflected and again gets internally reflected. So it has turned by 180 degrees. So you can turn the direction of light. Light which was coming towards you, it has been sent back via a prism. So all these are some beautiful applications of prisms and total internal reflection. So this surface has acted like a mirror. Even this surface has acted like a mirror. So designed a prism designed to bend light by 90 degrees or 180 degrees using the concept of total internal reflection. Another concept is the concept of optical fiber, where if you have a broadband connection, telephone connection, or in general, even the audio signals from your speakers of TV and all of that, they use these optical fibers because normal electrical, copper, aluminum wires, they can get interference from outside signals. They might lose some energy because of the resistance of the wire. Some wire touching happens, there is some cross connection which is happening, so all noise might come, some voltages might interfere, so there is a lot of disturbance and unwanted losses which might happen in regular wires like copper and aluminum. So the counter to that is optical fiber. Light will not get interfered because another light is passing. Light will not worry about electric currents. Light will not worry about magnetic fields. Light will just pass as if nothing bothers it. So using light, you can transmit signals. That that application is called as optical fiber. So inside that fiber, light will enter and it will get totally internally reflected until it exits out on the receiver side. And it is chosen, the material is chosen in such a way that it has very high refractive index. So whenever light falls, the angle of incidence is such that it is more than the critical angle, it gets internally reflected every time. And you can see the signal, whatever is there, the light information is being carried from one side to the other side. So they are made of high quality composite glass or quartz fibers, and basically the refractive index is higher than the cladding, and the signal goes from one end to a and gets repeated total internal reflections along the length of the cable until it comes out on the other side. Okay, so it prevents losses, it prevents interferences, it prevents unwanted noises inside the signal. That's the beauty of optical fibers, my dear warriors. Great. So that is what that is. Cool. Let's go to the next part. Okay, so that was a refraction, my dear warriors, at plane surface. Now we are going to go to refraction at curved surface. See, we just saw if you have a medium, this is the normal, then the light which enters will get refracted like this. This was angle of incidence, this was angle of refraction. This surface was basically a plane surface. But imagine a bubble, soap bubble, drop of water, or a glass which is curved, or a lens of a camera, or maybe any transparent material which has some curvature. That's a curved surface. So what happens then? So if you have a curved surface like this, some curved surface over here, okay, then what happens is as follows. Imagine this is that curved surface, this is that medium, then what you should do in such cases, if light is entering at a point, first of all draw a normal. Let's say our light was entering maybe like this. Then this particular angle becomes the angle of incidence, and the light will get refracted over here, and this will become the angle of refraction. Again, it will follow Snell's law over here. Observe one more thing, that this curved surface, this curved surface which you can see over here, I hope, also will have a center maybe somewhere over here, and it will also have some kind of radius of curvature. This is your radius of that curvature. This will be center of the curvature, and this point over here is then the pole. This point over here is then the pole, and this side might have some refractive index, let's say mu1. This side might have some refractive index, let's say mu2, and the light might get refracted depending on what is the value of mu1 and mu2. Are you able to see this? Are you able to visualize this? This is called as curved surface refraction. It also follows Snell's law. Obviously it has to, because every point on that curved surface is like a flat surface where you can apply our Snell's law. Beautiful, isn't it? Now imagine you have placed an object in front of such a curved surface. Then where the image will be formed will depend on what is the radius, what is the refractive index, where the object is placed, and so many things. And you have to do ray tracing, which is very difficult. So just like we did over here, where did it go? Yeah, we did ray tracing and seeing where the image might be formed. But that is obviously not what we intend to do in the exam, because you can't sit and draw rays and the angles might be crazy. So there is a formula for it to avoid the ray tracing. And the formula goes as follows, just putting it up over here. The formula is over here. N2 by V minus N1 by U is equal to N2 minus N1 by R. And using this formula, you can figure out where the actual image will be formed. Don't worry if you did not understand this particular formula, I'll explain this to you. Say, for example, and this is very, very important, just follow me over here carefully. This is some medium over here. Okay. And let's say the refractive index of this particular medium is, let's say, 3. Chumma I have taken some value, and the refractive index outside, it is basically 1. First things first, let's draw the pole. Pole is basically this midpoint. Okay, let's draw the principal axis which divides it equally. This is my principal axis. Okay, now I'm going to place my object. I'm going to place my object somewhere over here. Let's say this is where my object is. Okay, so this is my object. Okay, obviously object distance is always measured from the pole. So this is u. You will see where the rays are going, and maybe the image is formed somewhere here inside. Maybe Chumma I'm saying some random thing. Okay, this is where the image is. So definitely this is the image distance. Can you also see the curved surface? It will have a curvature. It will have a curvature. So this then will become the radius of curvature. This will become the center of curvature. Are you able to see that? Radius of curvature, center of curvature, and all of that. Clear, my dear warriors? Now, from the object, tell me, how will the rays come before refracting and making the image? The rays will basically come like this, right? They will go like this, right? So if the rays are going like that, pole is always the center. That means right side of the pole, that means this side is positive. Obviously the other side will be negative. Obviously the other side will be negative side. So clearly the object distance will be negative because it is on the negative side. The image distance will be positive. For the radius, check where the center is. It's on the positive side. So radius of curvature will be also positive. Sign convention clear? Everybody give me a thumbs up. Harish, as of now, there is no plan for that because usually students prefer 12th standard NCERT rather than 11th standard. But I know 11th standard NCERT is also important. That's why I've done the RNA series where I might not have done directly taking an NCERT in front of you, but whatever theory was there, in fact, more than that only have given for 11th topic-wise content in the RNA series. Okay, Harish? So if you're referring to my RNA series, trust me, you are doing more than what is required from NCERT. And anyways, in the board exam, 11th standard will not come. But yeah, from a NEET point of view, NCERT is important, which is already done as a part of RNA. Okay, now how the formula goes is this one. So let me write it down for you. It always goes second medium by image distance minus first medium by object distance is the difference of the refractive indices in the same order divided by the radius of curvature. So if you see over here what is exactly going to happen, first of all, refractive index of the second medium where the incident light comes, sorry, not incident, my bad, refracted. So sorry guys. This is second medium, that means it will be refracted. So this is where the incident light is going to be. Light is coming from the object, it is incident in this medium. So incident refractive index will be 1. This will be 1. Light goes into this medium whose refractive index is 3. So mu2 will be basically 3. Is this absolutely clear in everybody's head how mu2 and mu1 are decided? How refractive index 2 and refractive index 1 are decided, correct? Next, what about V and mu? We'll come to that, but before that, in the same order, put 3 and in the same order, put 1 over here. Now, coming to what is V and U and R. V will be positive, some positive number, I don't know, whatever it could be. U will be basically here, it will be negative U. So it will be basically negative whatever it is, example minus 3 centimeters or minus 10 centimeters or minus 20 centimeters, like that. And this V, you will get some value, I don't know, Chuma, I'm putting something plus 5 centimeters or, you know, or plus 17 centimeters, something after substituting, and radius of curvature. This one, it's positive, so you might get some value, maybe plus r, maybe something like this, maybe plus 8 centimeters or plus 10 centimeters, like that. So that will be given to you. Object distance will be given to you. Image distance will be asked, or image distance is given, object distance is asked. Main thing is substituting in this formula with the correct sign convention. All right, so this is that formula in which you have to substitute with the correct sign convention. If you do that, your job is done. Oh, in-text questions. So is it? Uh, I think the initial chapters, at least we had done it in the class, but we'll do one thing, Harish. When we do problem solving series, I will make sure that I will involve as many in-text questions also. Thank you for reminding me, but all right. So during the problem solving, which we'll be doing it in next couple of weeks, will involve more of in-text questions of 11th standard. Okay, no issues. So let's do a question on that. Let's do a question on that. Here is the question. Read it. Light from a point source in air falls on a spherical glass surface, and radius of this distance of the light source from the glass surface is 100 centimeter. At what position is the image formed? Okay, light from a point source of air falls on a spherical glass surface. Let's basically think about it. This is our spherical glass surface. It has its own radius of curvature. We also need to show the principal axis. This will be the positive side. This will be the negative side. Okay. Where is our object? Light source is over here. This is our object. From this object, light is coming out like this. It's going on this side. So that's why this side is positive, this side is negative. And this distance, object distance, will be how much? 100 centimeter, but negative 100. Negative 100 centimeters from the pole. Okay. I want to know where does it meet. And before going ahead, yes, this is the center of curvature. The radius of that curvature is 20 and it is on the positive side. So R is plus 20 centimeters. Refractive index over here is 1.5 and the refractive index over here is basically how much? 1, because it is air. Because it is air. Correct. Okay. Perfect. So let's apply our formula. Nothing great. So mu2 by V minus mu1 by U is equal to mu2 minus mu1 divided by R. That's it. All right. So let's start substituting everything one by one. What is mu2? Mu2 is where the refracted light will be. This is incident. It will refract into this medium, which has a refractive index of 1.5. So this will be 1.5. So I'll put 1.5 here. What is mu1? That is where incident light is. Incident light is in the air, so refractive index is 1. So I'll just put 1 over here. Radius of curvature, as you can see, is plus 20. So put plus 20. Object distance is basically negative 100. So just put minus 100. Image distance is what I do not know. Now you just need to solve this equation and I'm pretty sure you'll get the answer. Okay, solve this and see what is the answer that you get. If you want, you can just shift it over here. So 1.5 by V is equal to 1.5 minus 1 is 0.5. So 0.5 by 20. Negative, negative, positive goes on the other side, becomes again negative. So 1 by 100. All right, 1.5 is 3 by 2V is equal to 0.5 is half. So 1 by 40. 1 by 40 minus 1 by 100. Obviously, we have to take the LCM of 100 and 40. Actually, before doing that, let's cancel 2 everywhere. So 3 by V is equal to 1 by 20 minus 1 by 50. Now LCM of 20 and 50, that's going to be 100. 20 goes with 100 5 times, 50 goes with 100 2 times. So it will be 3 by 100. 3 cancels. So 3 by V is equal to 3 by 100. 3 cancels. So V will be basically 100 centimeters. Yes, that is what it is, and it is positive, which means the image will be formed on this side. And if it is formed here, obviously the rays will meet. Obviously the rays will meet. So that means there will be a real image which will be formed. Real image. This side will be real, this side will be virtual. Be careful. Yeah. Yes, Koku Shibu, I'll be doing it in 2 lectures, definitely. Because one lecture is little tough, not for me, but from students' point of view also, because there are many concepts in this. It's a big chapter. I don't want to hurry up just for the sake of it. Okay, clear till this point? Great. So we have figured that out. All right. So in this particular part, refraction by a lens is something like where you have two refracting surfaces. So if you talk about something like this, where let's just go to the physics simulations in the FET and let's see over here. Yep. So this is just a lens. There we go. A lens can either bend the rays by converging, or it can even diverge the rays by pushing them away. This kind of lenses are called as concave lenses. You can see that. You can see these lenses are concave. They are caved in, whereas when they bulge out, that is called as basically convex lens. Okay, so this is a convex when it bulges, and the convex lenses are converging kind of lenses, and concave lenses are usually the diverging kind of lenses. And in these kind of lenses, you will see there are two surfaces where the light will refract. So there are two refractions happening, and that is why this has been kept after the single curved surface refraction discussion. We had discussed this particular formula and this phenomena. So this has been kept after that. So what exactly happens? What's the formula like, and what are the different, magnification formulas, etc. See, let me tell you very clearly over here. When you talk about a lens, let's say for example, this is one surface, this is another surface. This is a structure of a lens, let's say. This is the center, which is also your pole. Okay, this is your center, which is also your pole. And now let's say I divide the lens into two equal halves. That line is then called obviously as the principal axis. Principal axis. Let's say there was an object which is placed over here. Let's say there was an object which is placed over here. So then this will be the object distance or object coordinate or distance. That's how it is called, u. So the rays from that particular object, will enter the lens over here. And at this very particular point, what you will see is that it will get refracted. So how will it get refracted? I need to draw a normal. So if I draw a normal, something like this, maybe this is how the normal will be. Okay, the ray will obviously bend now. The ray will obviously bend now towards the normal because it is entering a denser medium. Now comes the next surface. At that next surface, to see how it bends, again I need to draw another normal over here. Let's say, over here something like this, or I don't know, Chumar just drawing it like this. Okay, great. So this is another normal which is drawn. Okay, and then the light ray, because it is going from dense to rare, it will bend away from the normal maybe, and let's say the ray meets over here. Now this is just one of those rays. Now there will be many more such rays which I can draw at different places, of course. Maybe one more ray here, maybe one more ray somewhere else, and so on and so forth. I'm just showing some few more rays just for your understanding over here. Okay, and maybe it meets over here, then maybe some more rays over here, then maybe, wow, it's like this, let's say, and it's over here. So you can see the rays are meeting over here. So that means this is the location where our image is formed. And then this particular distance is nothing but V, and it is also called as your image distance or image coordinate or image distance. Is that right? Everything is measured from the pole. So that is how ray tracing is done to figure out where the image will be formed because of a lens. And you can see there are two surfaces which are there over here, and the refraction happens at both those surfaces. This particular one over here, this is basically your first surface where the refraction occurs. So this line, the dotted line that I have drawn for that surface, this is basically the center of curvature, number one. And that line becomes the radius of curvature labeled R1. This is the radius of curvature of the first surface where the light rays will refract. Are you able to visualize and understand this? The light rays hit this surface, and over here using Snell's law and the curved surface refraction, it bent. So if I draw a normal, obviously for a circular arc, the perpendicular drawn becomes the radius. This becomes the center of that imaginary circle. So that is the center of curvature 1. This is R1. And this is basically your first surface. This is the second surface, like you can see. This is basically your second surface, like you can see, my dear students. And for this particular surface, when you draw the normal, that also becomes the radius of this particular imaginary circle, So therefore, this will become your center of curvature 2, and this will become your radius of curvature labeled 2. Are these nomenclatures clear in your head? Are these nomenclatures absolutely clear in your head, my dear audience? If this much is clear, then, sir, what is the formula, sir, finally? What is the formula that you get, basically? So the formulas that you get are as follows. The first things first, the 1 by image distance and 1 by object distance is equal to 1 by f was very much similar in the case of a curved mirror, but in the case of a curved mirror, it was a plus. Here, the sign will be different, it will be negative. 1 by image distance, 1 by object distance, negative sign is equal to 1 by the focal length. Yep, that is the first formula, which is also called as your lens formula. This is also called, what is this called? This is also called as your lens formula. Lens formula to locate images, to locate basically an image. You can also check the magnification, which is also the height of the image upon height of the object. This formula, very similar to the mirror formula. Instead of negative V by U, the sign will change. Wherever minus is there, plus will come. If plus is there, minus will come. So this will be plus V by U. That's the major difference. So this is basically your magnification. This is nothing but your magnification formula. This is magnification formula. The same theory which we have learned before is still applicable here also. So, for example, if magnification is positive, that means the image is going to be erect. And if the magnification is going to be negative, that means the image is going to be inverted. It is going to be upside down. That's the sign of the magnification, which will come depending on the sign of V and U. Remember, V, U are sign sensitive. Yep, they are sign sensitive. So you have to use your sign convention. And we have seen how the sign convention works. Yep, wherever the incident rays are moving, that side of that lens or the mirror becomes positive. So that means this side obviously will become the positive side. This will become the positive side, and obviously then this side will become the negative side. This is as per the sign convention. So remember this sign convention as before. Sign convention is as before. Okay, as before. So always incident direction incident direction is considered as positive, and upward direction is also considered as positive. Anything on the top is positive, anything below is considered negative. No, they will not ask you derivations in the exam. Sri Lakshmi, I'm not sure how long will the session go. Sir, but there is one problem, sir. You'll be like, what? Sir, in mirrors, F was related to the radius. What was the formula? Come on, put it up in the chat box. What was the relation between radius of curvature and the focal length of a curved mirror? R and F. F focal point was the midpoint of center and the pole. So R was 2 times the focal length. Remember that? Yep, correct. Hi Suparna, good morning. Yes. Here, is R going to be 2 times of F? No. First of all, there are two radius. There are two surfaces. So there are two radius of curvature. Oh, number one. Number two, I think it will also depend on what is filled inside. That means the refractive index of this particular lens. Yes, the refractive index of this particular lens will also matter. That means mu, the value of mu relative to the relative refractive index of the lens with respect to the medium outside, whether the lens is kept in water, glycerin, kerosene, petrol, alcohol, some other liquid, who knows. So the relative refractive index, because the light rays will bend accordingly, so that will also matter. So the actual formula for the focal length comes out like this: 1 by the focal length of the lens is refractive index of the lens with respect to the outside medium minus 1, the whole thing, into 1 by R1 minus 1 by R2. This is the formula. If you're wondering what is this, this is relative refractive index. So this is the refractive index of the lens by refractive index of the medium. If the medium is air, then this mu m will be just 1. So you will just put the absolute refractive index of the lens. If the refractive index is air of outside medium, the refractive index of outside medium, if it is air, it will be 1. So anything by 1 will be that anything. So you can just put that absolute refractive index. If it is glass, put directly over here 1.5. That's how it works. R1, R2, you have to follow the sign convention. R1, R2, you have to follow the sign convention. So this is the formula. And if you're wondering what it is called, well, it is called as the lens maker's formula. The lens maker's formula. Why? If somebody has to design a lens of a particular focal length, and if they know what material they are getting, or if they have a choice of material, they can select mu R1 and R2 to design a lens of a particular focal length. So that's why it is also called the lens maker's formula. Got it? Very good. Awesomeness. Let's try to do a simple question on this so that you get an idea. Let's see what kind of question they have kept. Okay. Okay, this is different. Okay, wait a minute. This is different. No, we'll do separate examples so that we can build the concept. Let's build the concept, my dear warriors. Let's say I have a concave lens. I have a concave lens. This is, let's say, 10 centimeter. This is, let's say, 5 centimeter. This is having a refractive index of 1.5. Can you find the focal length? Can you find the focal length of this particular lens? Let's try to figure this out. It's not that difficult. So in order to find the focal length, the formula that we have is 1 by f is equal to mu length refractive index with respect to the medium minus 1 by r1 minus 1 by r2. Okay, fine, sir. What is the refractive index of the outside medium? It is air. If outside medium is air, the refractive index of air is just 1. This will just become 1.5. You can just divide it by 1. It won't make a difference. Okay. Now, what is this R1 and what is this R2? Be very, very careful. See, light rays will go here. So, wherever that light rays go, that side becomes the positive side, and the exact opposite side becomes the negative side. Now you need to understand who is R1, who is R2. For that, you should know who is the first surface, who is the second surface. If the light rays are coming from here, this is the first surface. So therefore, this would be center of curvature 1 and this would be R1. If light rays enter this surface next, so this would be the second center of curvature. That means the second radius of curvature will be 5 centimeters. Got it? How light hits the surface? In that order, you will label them surface 1 and surface 2. Accordingly, for that surface, that radius 1 and center 1, that radius 2, and that guy's center number 2. Yes. Yeah, we'll come to example 9.7, everything. Hold on. Okay, now check this out. R1, should it be positive or negative? Well, it is on the negative side, so that's why it will be negative 10. R2, it is on the positive side, that's why it will be plus 5. That is how the sign convention will work. So therefore, what I will write, 1 by f is equal to 1.5 minus 1 is basically 0.5. Okay, this is negative and negative, both negatives together. I will take that negative sign common. So it will be 1 by 10 plus 1 by 5, which can be written down with LCM as 10, 1 plus 2 by 10, which is basically 3 by 10. 3 by 10 over here. 0.5 is nothing but half. 0.5 is nothing but half. Okay, so this will just become minus 3 by 20, that is 1 by f. So the focal length is negative 20 by 3. Focal length is negative 20 by 3 centimeters. That is the answer. Everybody understood? Is this absolutely clear? Yes, that's how the sign convention is. Correct. Yes, definitely, Sukanya. Some question problem solving series with PYQs, everything is coming. Now, the meaning of the word negative is that for this particular lens, which is there, if the rays were like this, parallelly incident, they will obviously diverge. If one extends them backwards, they will meet here. This particular distance is basically 20 by 3 centimeter in absolute terms. So that is why the focal length is negative, because this side is always negative and this side will be the positive side. So for concave lens diverging in nature, the focal lengths are negative. I hope this is absolutely clear. We will do one more example so that you guys get a hang of it. Imagine you have been given something like a lens like this. Okay, a lens like this. It's a plano-convex lens, and it has been told to you this is basically 20 centimeters. This is, let's say, for example, having a refractive index of 1.6 or something, and the outside medium, the medium outside has a refractive index of 1.2. Okay, so there is a refractive index. Then you have placed an object over here. You have placed an object over here at a distance of 40 centimeters. At a distance of 40 centimeters. The questions are as follows. Find what is the focal length. What is the focal length? Number 2, the image nature. and characteristics, where it is formed, how it is formed, what is the magnification, is it inverted, is it uh, erect, enlarged, all these things. That's what we are trying to figure out. Okay. Yes, no issues. Harish, I will anyways not be doing NCRT for modern physics because doing NCRT for modern physics doesn't make sense also because it is anyways a little bit theoretical, postulates, all those things are there. And from the NEET perspective, I think we have to approach it in a completely different way. So, anyways, wave optics will be my last class for NCRT line by line series. That would be next week. After that, modern physics, whenever I do it in a different way, I will approach it differently. Okay, and we will cover it up. Anyways, you can watch my Super 6 classes also, my last year classes, in case you want it. But if you can wait for some time, that would be really great as well. Okay, so shall we do this particular question, my dear warriors? Okay, let's do this. It's a plano-convex lens. Keep that in mind. Oh, for a plano-convex lens, you have to be little bit more careful because see what will happen. I'll tell you. This is the first surface. This is the second surface. For the second surface, this is the radius. This is the center of curvature. So the radius of curvature number 2 is this. But for the first surface, where is the radius? Where is the center? Because it is not even curved. So what should you take? Let me tell you that when something is curved more, the radius is less. As it curves less, the radius becomes more. And when something becomes flat, the radius becomes infinity, infinitely large, because now this circle is big, this circle was small, even big circle, this will be infinitely large circle. Infinitely large circle means the radius of curvature is infinity. So that means the radius of curvature number 1 is infinity. You cannot locate its center. It's one of the biggest circles ever because flat surface has infinite radius. Got it? This concept has to be entering, it should be there in your head. Okay, fine, sir. So, sir, what is the focal length answer, sir? Let's find out. It is mu minus 1 by R1 minus 1 by R2. Okay, 1 by F. Okay, sir, but we need our sign conventions. Yes, sorted. Okay, so this is the positive side, perfecto. And this, obviously, everything on this side, oops, everything on this side is negative. Oh my God, this is negative. Okay, fair enough. So what is the refractive index of the lens with respect to the medium? Refractive index of the lens 1.6 upon refractive index of the medium 1.2 minus 1. Okay, 1 by radius 1. Radius 1 is infinity minus 1 by radius number 2. Second surface's radius is 20, but will it be positive or negative? That radius is on the negative side, so it should be minus 20. This is the catch. Be careful about the sign conventions. Everybody fine till this point? Okay. So what is next? Let's find out. 1 by f is equal to 1.6 by 1.2 is 16 by 12. 16 and 12 both are divisible by 4. 16 goes with 4 times. 12 goes with 4 3 times minus 1. What is 1 by infinity? See, when you divide it with a large number, the answer becomes small. When you divide it with the largest number, the answer will become the smallest. So 1 by infinitely large, the answer will be tending towards 0. So you can put 0 over here. Minus minus becomes plus. So plus 1 by 20. Okay, sir. So 1 by f is equal to 4 by 3 minus 1 will just become 1 by 3 over here, and this will just become 1 by 20 over here. So therefore f will become 3 multiplied by 20, or f will just become 60 centimeters. The focal length will just come out to be 60 centimeters. First job has been done. We had to figure out what is the focal length. That job has been absolutely done. Now the next job, we'll figure out where the image is going to be formed. 1 by v minus 1 by u is equal to 1 by f. What is image distance? I don't know. What is object distance? It's clearly mentioned. It is 40 centimeters, but it is on the negative side. So minus 40, 1 by F, 1 by 60. Okay. So 1 by V is equal to minus minus is plus. So when it goes on the other side, again it will become minus. Take the LCM of 60 and 40, that is 120. 60 goes with 120 two times, 40 goes basically 3 times. 2 minus 3 is negative 1 by 120. Therefore, V will be negative 120 centimeters, number one. Next, let's also find the magnification. Magnification is V by U. V is minus 120. U is a negative 40. So basically negative negative cancels and we will get it as 3 units. We'll get it basically as 3 units. From this, what do we conclude? The image is first of all on the negative side, means it is over here. This side will be virtual. This side, because the rays can converge, will be real. So image is virtual at 120 centimeters from the lens. Not just that, you can see the magnification is positive. That means it is erect, it is not inverted. And it is 3, that means it has been magnified or it has been also enlarged in nature. So you will see an enlarged image, erect image, as well as virtual image because of this particular setup. Yes, definitely it is useful for your board exam. Why else will I do this? Okay, fair enough. How to solve these questions? Right. Now, the last thing which we have to deal over here. Okay. All this is done. This is done. This is done. Last thing. Remember, so all these things, let me just mark it over here, whatever we have just done. So refraction by lens. Okay. So here the first refracting surface forms an image 1 from the object. The image 1 acts as an object for the other surface that forms the final image. So using these formulas, we basically get this 1 by V is equal minus 1 by U is equal to 1 by F. And also these are the rules used for ray tracing, like a ray which is parallel to the principal axis after refraction passes through the focus. A ray which passes through the center of the lens emerges without any deviation. A ray which passes through the first focus will emerge parallel to the focus. A ray which is parallel, similarly, a ray of light which is incident on the concave lens appearing to meet on the principal axis on the second emerges parallel. So these are the rules used for ray tracing, just like we used it for mirrors as well. I'll just explain this to you. If a ray is parallel to the principal axis, what will happen? It will pass through the focus. That's it. Simple. But remember one thing, that in case of a lens, usually we have two kinds of focus, the actual focus and a point similar to the focus on the other side. Okay, instead of light coming from here, if the light went from here, where would the light meet? It would meet here. So that is also called as the second focus. So that's why you will see usually this term that the focus is where the light will actually meet, and you also have it on the other side called as the secondary focus. So there are two focuses usually for the lenses. Okay, if a light passes through the focus which is secondary, then it will become parallel. It makes sense, because if the light came parallel from here, then it would pass from the focus over here. That also makes sense. Reversibility principle. Last thing is, if the light passes through the center of this particular lens, then it will pass as it is without getting deviated. The same things are also true for a concave lens. So if a light passes through the center, it will definitely pass undeviated. It will not deviate at all. If a light is parallel, it will deviate in such a way that when you extend it, it will appear to diverge from the original focus, and the secondary focus is this point over here. So if a light is incident towards the secondary focus, it will become parallel. It makes sense, because if light were to come from here, then it will diverge like this, and it will appear to diverge from the focal point. So these are the rules used for ray tracing. These are the rules used for ray tracing. Not much useful for neat perspective, but I have just told it to you. These were things which you have learned back in the 10th standard. This was the magnification formula. And remember, you have to apply the sign convention that for erect, M is positive, and for inverted, the M is negative. We have already discussed that, all these things. Last things over here, before we go ahead, power of a lens. Power of a lens, the formula goes like this. It is 1 by F. Yep, it is 1 by F. Now, what is the meaning of power? Power is nothing but it is a measure of how much does it converge or diverge. So when you have a convex lens, the rays converge. When you have a concave lens, the rays diverge. So how much is the convergingness or divergingness? That is decided by the power. So imagine if the rays of light meet over here versus the rays of light meet over here. This has less focal length, this has more focal length. Because it is converging earlier, it has more power. Here it is converging later, so it has less power. So that is why it is reciprocal. If the focal length is less, the power is more. If the focal length is more, the power is going to be less. Got it, my dear warriors? Why it is 1 by F? More focal length, it will have definitely less power. Is this absolutely clear, everyone, till this particular point? Okay. Now, also remember, the power can be positive or negative. If the rays converge, then it is positive. If the rays diverge, then the power is going to be negative. That is also something which you should keep in mind. So I think all these pointers will be mentioned over here. Yep, let's see that. So basically, yes, the power of a lens is positive for a converging lens, whereas it is negative for a diverging lens. Also, what is the unit of power? What is the unit of power? The unit of power is basically diopter, and only when the focal length is in meters. If it is in centimeters, please convert it into meters. Convert it into meters before measuring that power. Example, if the focal length is 40 centimeters, if the focal length is 40 centimeters, the power will become 2.5 diopters, because 40 centimeters is 0.4 meter. So which means 1 by 0.4, which is nothing but 4 by 10, which is nothing but 5 by 2, which is nothing but 2.5. So 2.5 diopters will be the power of the lens. And because the focal length was positive, the power is also positive. If the power is positive, that means it is converging type of lens, more like a convex lens. Is this clear? Hostel facility, I think, is available through our contacts, not directly, but we have some kind of tie-ups. So if you are a NEET repeater, you can definitely visit the Vedantu Learning Center in Chennai or Madurai or wherever you are, and try to connect with the counseling staff. They will help you with the accommodation as well. Yep, if you're especially NEET repeater. Okay, so a magician during a show makes a glass lens with some refractive index of 1.47 disappear in a trough of liquid. What is the refractive index of the liquid? Could the liquid be water? Now, you might have seen this. A magician during a show makes a glass lens with some disappear in a liquid. So imagine there is a lens over here, and you have a beaker or something like this over here, and what happens is you pour some liquid into this. You pour some liquid into this, and as soon as you pour some liquid, this lens should basically disappear. How will that happen? This can only happen in one particular scenario, if the refractive indices basically have to match. Then you will not see any blurriness or any kind of deviation or any kind of distortions when the light rays will enter and exit through the lens and the medium. If the refractive indices were different, then the rays will get distorted and you will feel, okay, something is wrong over here. Imagine something of the same refractive index, the light won't bend. So there is no way you can tell that something actually is there. Your eyes will be deceived. So that is the reason why you will make sure that the refractive index is very much similar to that of the outside medium, and that's how you can make it disappear. Is the liquid water? No. In fact, usually it is glycerine, because the lens refractive index and the glycerine's refractive index are roughly similar, because 1.47 is roughly also the refractive index of glycerine. Is that okay? So that is the trick which is used. Example 9.7. In this, the focal length of 0.5 meter, what is the power of the lens? Very straightforward, guys. Power is 1 by f. Power is nothing but 1 by f. So 1 by 0.5, which means it is 2 diopters. Yes, it is 2 diopters. Perfect. So this is definitely done. Next, the radius of curvature of a convex lens are 10 centimeter and 15. Focal length is 12. What is the refractive index? So you know the focal length, you don't know the refractive index. Exact opposite. So use 1 by f is refractive index minus 1, 1 by r1 minus 1 by r2. But you have to make sure that the sign convention is also followed properly. So if this is the convex lens, this is the this is the second radius, because this will be the second surface. This is the first surface. So the center of curvature 1 will be here, and the radius of curvature are basically what? 10 centimeters and how much? 15 centimeters. Yes, this is 15 centimeters. This is the negative side. This is the positive side. So 1 by focal length. What is the focal length? Focal length is 12. So 1 by 12 is refractive index minus 1. 1 by R1. What is R1? Plus 10. Minus 1 by R2. What is R2? It's not 15. It's on the negative side. So minus 15. Solve this. You will get N as, or the refractive index as 1.5. Understood how to solve this particular question? Solved example. In-text questions are very important. Okay, very good. Awesomeness. For a glass lens in air, okay, now, so that was the second part of it. That was the second part of it. If that convex lens has 20 centimeters focal length in air, what will be the focal length in water? Okay, so how to do this particular question? If a convex lens has 20 focal length in air, how much focal length will be in water? Water's refractive index is given. See, 1 by f is mu minus 1, 1 by r1 minus 1 by r2. When you change the outside medium, this particular part will always remain a constant. Only thing that will change is this. So therefore, 1 by focal length in air upon 1 by focal length in water, what you will do, this will be refractive index of the lens in air. So refractive index basically just of the lens in air minus 1. Here inside water, it is the refractive index of the lens with respect to the water minus 1. That's the major difference. So focal length of water by focal length in air is equal to refractive index of the lens. What is the refractive index of the lens? Yes, it is 1.5. It's a glass refractive index. And refractive index of water is 1.33, which is 4 by 3. So you can write it as 1.5 divided by 4 by 3 minus 1. Okay. In air, what was the refractive index? It was 20. So focal length in water by 20 is equal to 1.5 minus 1 is 0.5. 0.5 is 1 by 2. 1.5 is 3 by 2. 3 3s are 9. 2 4s are 8 minus 1, which is 1 by 2. 9 minus 8 is 1. 1 by 8. So that will be basically 8 by 2, which is basically 4. Okay, so focal length in water is 20 multiplied by 4, which is 80 centimeters. So around that is what you are going to get. Here they have used 1.33, they have not used 4 by 3, that's why they have got it as 78.2, but our answer is very much close to 78.2. So that's how you do the third question. Is this clear? How to solve this example? Yeah. Noted, Jagannath. All right, moving on to the next concept of combination of lenses. Imagine two or more lenses are touching each other. When two or more lenses are touching each other, we cannot do this. We'll use the first lens, find where the image is, then again make that image as the object for the next lens and find where the image is, then make that image as the object for the next lens and find where the image is. It will be a repetitive process. I don't want to do that. Instead, can we combine all the lenses into one single lens when multiple lenses are in contact? Yeah, so that is very, very important. So when you have several thin lenses of focal length f1, f2, f3 and they are in contact, both the words are important. Several thin lenses are in contact. Why this word is important is because there was a question once like this which said there is a convex lens. Let's say the focal length of that particular convex lens is plus, I don't know, 25 centimeters. And then there is a concave lens of, let's say, focal length minus 10 centimeters. And it was given that if a parallel beam of light, they are not in contact by the way, if a parallel beam of light enters here, it exits also parallelly. So if that is the situation, can you figure out what is that? Can you figure out what is the distance between the lenses? Can you figure out what is the distance between the lenses? This was one of the questions. And this is asked in multiple competitive examinations. Now over here, obviously the lenses are not in contact. Obviously the lenses are not in contact. The lenses are not in contact. So how do you do such a question? I'll tell you what, it's a very straightforward trick over here. Think like this. After the first refraction from the convex lens, because the rays are parallel, they will definitely meet. Where will they meet? They will meet at the focal point. But since I want the rays to be parallel after concave lens, what if I ask these rays to meet at the focal point of the concave lens? Just imagine this. Right now, this particular distance is 25 centimeters. They are trying to meet over here. But I ask it to meet at such a point by placing the concave lens, which also becomes the focal point of the concave lens. We know the rule. What happens? If the rays are meeting towards the focus for a concave lens, they will end up being parallel. So you can see the rays will become parallel. Actually speaking, they won't even actually reach till there. So I should ideally show this as dotted lines. Yes, I should ideally show this as dotted lines. That's what will happen, which means this particular distance, which you can see right over here, this one, yep, that is the focal length of the concave lens, which is nothing but 10 centimeters. So if this is 10, this is 25. Can't we just figure out how much this distance will be now? Yep, this is going to be 25 minus 10. So it will be 25 minus 10, which means it will be 15 centimeters. That is the answer. So this is the correct answer for this particular question. The lenses were not in contact. Is this okay? All right. So coming back over here, in this, the essential criteria is the lenses are thin. Yes, that's anyways the criteria, but they are also in contact. So all lenses, multiple lenses, you can convert it into a single lens of effective focal length and effective power also. What's the formula? Always the powers get added the focal length reciprocals get added. So the net power is P1 plus P2 plus P3, whereas the focal lengths get added like resistors in parallel. So P is P1 plus P2 plus P3. 1 by F is 1 by F1 plus 1 by F2 plus 1 by F3. That is what it is. Okay. So that is again very important here. P is the net power of the lengths combination. Okay. And individual powers may be positive and even negative. So be careful about that. So some of the terms on the right hand side may be positive, like say for convex lenses, and some of the negative terms might be there for concave lenses. Okay. Also, the last thing, the net magnification, because each lens will try to magnify, may try to zoom it, may try to zoom it in. So the net magnification is given by the product of all the magnifications, M1 into M2 into M3 into M4, like that. So that is how you get the net magnification. So the total magnification M of the combination is a product of all the magnifications of individual lenses. That is something which you should keep in mind. Let's have a look at the question which is there on this. Find the position of the image which is formed over here in this particular question. But the funny part is, these lenses might be thin, but they are not in contact. These lenses might be thin, but they are not in contact. So the funny part is, you cannot use this particular formula at all. If you had to use this formula, it had to be a question like this. Let's say there is a lens here, there is a lens here like this. Let's say the focal length is 20 centimeters. The next focal length is, let's say, minus 40 centimeters. Okay, can you find the effective power of both the lenses? Let's say this was the question. I will be like, yes, definitely. Since both these lenses have different focal length and I can combine them into one singular lens. First of all, 1 by F effective is 1 by F1 plus 1 by F2. So what is F1? F1 is 20. What is F2? It is minus 40. So it will be 1 by, or basically LCM I can take it as 40. So it will be 40 over here. This will become 2 minus 1. 2 minus 1 is just 1. So it will just become 1 by 40. That is 1 by F effective. You can also write this as effective focal length is just 40 centimeters, which is 0.4 meter. But I want effective power, which will be 1 by F effective, which is 1 by 0.4, which is 1 by 4 by 10. So 10 by 4 is nothing but 5 by 2, which is 2.5 diopters. So the effective power is 2.5 diopters. Correct. So that is the effective power of the lens. This can be used if the lenses are in contact. But in the NCERT solved example in text question, the lenses are not in contact. You can see there is a gap of 5 centimeters from 10 centimeters between the lenses. So what you do is you take the first lens, object distance as 30 with negative sign, find where the image is. See, they have used lens formula. 1 by V minus 1 by U is 1 by F. Focal length is given to be 10. Object distance negative 30. They found the image to be at 15 centimeters. And that is coming out 15 from the first lens. So from the first lens, if it is at 15 centimeters, for the in-between lens, because already the gap between both of them is 5. Oops. The gap between both of them is 5, which means actual distance from the second lens will be 15 minus 5, which is 10 centimeters. So for the next lens, what will happen? The image of the first lens will now become the object for the second lens. And that object will be not at 15, it will be at 10 centimeters because of this 5 centimeters gap. So that is what you will see will be done in the next part. You can see object distance is 10, the focal length is negative 10, 1 by V minus 1 by U is 1 by F. Surprisingly, what happens is the answer for that comes out to be as infinity. Now, the moment the answer comes out as infinity, don't get scared. It means the rays have just become parallel. It just means the rays have just become parallel. The image is not formed. Yes, the rays are not meeting. That's why you can say the rays have become parallel. If the rays become parallel and they pass through a convex lens, what will happen? They will definitely meet at the focal point, and the focal length is 30. So they will definitely meet at 30 centimeters, like you can see. So that's why the final image will be formed at 30 centimeters from the last lens. But if you actually measure it from the object, this 30, this 5, this 10, and this 30, all of them to be added. So 30 plus 5, 35 plus 10, 45, 45 plus 30, that is going to be 75. So 75 centimeters from the object, that's where the final image will be formed. That's how you solve this particular question. Is that okay? Shall we go ahead? All right. So we are coming towards the prism part now. We are coming towards the prism. Let's get ready. I think we might have the prism simulations. By the way, you should play around with this a lot. You will get a feeling of how the lenses magnification, everything works. When the object is far, you can see the image is highly diminished. It's formed near the focus. As you bring it closer and closer and closer, the image becomes enlarged slowly, but it is still smaller than the original object. But it is inverted until you make it go towards the focus. Once you go towards the focus, you will see that's it. It is not formed because the rays will become parallel. After this point, I'm not able to change it. After this point is where the image will be enlarged. As you can see, there is a virtual enlarged image of that particular, pencil which is formed over here. This is virtual. This was real because the rays are meeting at this point. That is what happens for a convex lens. For a concave lens, the image is always diminished over here in front and it is erect, even though you bring it here. Yes, you can see it is diminished, erect image, and it is also virtual in nature. That means you will have to see from here. You will see this object over here. You will see a small object's image over here. Yeah. Whereas if you use a convex lens, you will not be able to see it unless this is over here. You will see, if you see using this lens, you will see a big image of this particular object. Okay. I hope this is absolutely clear. Which part, Shri? Which part you want? Let me know. Now let's talk about lenses. What do you say? Prisms as well. Let's come to prism. I think prism was also there, but where did prism go? Over here. Yes. Okay. So finally, we have come to prism. Now, what's a prism? Prism, a lot of people think it should be triangular. No. A prism means you have two surfaces which are at an angle to each other. Imagine there is one surface here, there is another surface here. They are parallel. Then it becomes like a normal glass slab. But if the surfaces are like this, like this, like this, like this, like this, something, making an angle, that object is called as a prism. Basically, two surfaces refraction, flat surfaces, but at an angle. Yeah. All right. So, as you can see over here, my dear students, imagine this light which was normally going over here. If I introduce a glass kind of prism over here, you can see the light will bend so beautifully and it has refracted here as well as here. I can also make that light fall at different places. In fact, even at different angles as well. Let me just turn it. Yep. I can make this go like this at different angles and it will definitely deviate and bend also by different amounts. I can also turn the prism and you will see that if the angles change, you will see that even the refracted ray which emerges out also will definitely change. We can also have a beam of light to see how exactly it goes to get a more clearer picture. So if I change this, you can see how the light rays will, bend when different angles of incidences are there, or I can even change this over here beautifully, correct? So that's what basically a prism is. Now, instead of this, if I use this, that is also a prism, because you still have two surfaces. Even if the top is missing, don't worry, it is still going to be a prism. But if I use this, this is not a prism because both the surfaces are parallel. This is a slab. You will see that the ray of light, which is there, it is coming out parallelly. No matter what you do, the ray of light will always come out parallelly. But it's only the case of the prism where the ray of light is not parallel to the incident, it is at an angle, it emerges at an angle. So that's why we study prisms differently. So this is also a beautiful exercise. This is just a lens, okay? This is not a prism, of course. So you can also have multiple prisms combination. So if you have two prisms like this, then you can see it will be deviated multiple times. I can also make it go opposite like this. You can see it deviated here and again it went there. So you can keep as many prisms as possible, and you can make the light go whichever way you want by arranging these prisms at different angles, and you can deviate how much ever you want them to be. So that is beautiful application of prisms, and it is used in your camera lenses and all of that. Okay, I hope this is clear, my dear students. Okay, 9.6, which part of 9.6? Sorry, you said 9.8, my bad. In 9.8, see, I just told, I don't know whether you're able to see those lenses. There is one lens over here. This is the object number 1 that is forming the image over here by lens formula at 15 centimeters. That image for the next lens which is there becomes the object, because there is a gap of 5 centimeters from that lens. The object's distance will be 10 centimeters. So object distance is 10 centimeters, and using lens formula again, the image came out to be at infinity. So the final image due to this middle lens I2 is basically at infinity, meaning the rays of light are just simply parallel. And whenever rays of light are parallel, then what happens? They will converge or diverge depending on the type of the lens. So for the third lens, which was convex in nature, the rays basically just met at this particular point, which is the focal point, which definitely will be 30 centimeters. So that's why the final image is formed at 30 centimeters. You just have to use the lens formula multiple times for each of the lenses. Is that okay? Thank you for all the fire, Krishna and Disha. Thank you so much. Now, the formulas that you should know and the terminologies that you should know for a lens. Number 1, the angle between the refracting surfaces is A, which is also called as the prism angle, or the angle of prism, or the refracting angle of the prism. I think it will be mentioned somewhere. Maybe not here. Okay, it's not mentioned. Anyways, no issues. I'm glad, MC, you understood. Hi, sir. I'm new to the class. My name is Lalita Priya. Welcome, Lalita. I hope you are enjoying the class and loving those simulations as well as understanding all these examples and theory as well. Keep it up and stay subscribed and keep watching all the videos. And also, we are starting off with station 0 of your NEET Express, and something really big is going to happen in the NEET Express as well. Okay. Now, this is your incident ray. It refracts and refracts. This is called incident ray. The ray which finally comes out is called emergent ray. There are some angles which are marked over here. This is the angle of incidence I. The final angle by which it comes out, this is emergent angle. You can see E is the symbol used for that. Internally, when you draw the normals, there will be some angles which will be formed by those rays. With the normals, they are called R1 and R2, as you can see over here. Okay, R1 and R2. This particular ray will deviate by some angle, meaning the ray was supposed to go here, but it ended up going here. So if you extend it backwards, this is the angle by which it has deviated. The symbol for that is delta, as you can see over here. So what's the relation between this deviation and the other angles? First important relationship, delta is I plus E minus A. Angle of deviation is incident angle plus emergent angle minus the angle of prism. This is the first relationship. Hello Arni, welcome. Welcome. A lot of people new to the class. Nice to know all of you. Some of the people forget to mention, sir, I'm new. It's good that you are telling me that, sir, I'm new. Yep. That way I will know you. Yeah, or else you will go unnoticed. So this is the relation between incident angle, emergent angle, angle of prism, and the deviation angle. That means coming back over here, let's get rid of these things. I don't want it. So as you can see over here, can I draw normals? Yes, I can draw normals. Do you see over here that this angle, can I zoom into this? No, I can't. This angle is the incident angle. This angle is the emergent angle. If you see, the ray was going like this, but it ended up going like this. So this is the deviation. This is the angle of the prism. That's the terminologies which have been used. Next important point, which is not mentioned here, but I will give it to you right over here. The internal angles which are there, R1 and R2, if you add them, guess what? You will get the angle of prism. You will also get the angle of prism. So R1 plus R2 is another important relationship that everybody must know. Yeah. Welcome aboard. Welcome aboard, Thinasari. Yes, all the new Pandus and Champas to the class. Okay. Now, there is a interesting thing that happens. If you see, this is our prism. I can't do anything with it. Okay. I just wanted to make it a little bit bigger, but unfortunately, I can't make it big. It's okay. Now, what I will do is, I will make the light fall at different angles and I will see how much it is deviating by. So let's say right now, as you can see, the angle of incidence is very large. Can you see? It's like 85, 90 degrees almost. From the normal, if you measure the incident angle, it is very large. So it is deviating this much. Now, if I make the light fall, my goodness, almost like this, it is almost getting internally reflected. So not all the angles are permissible. So as you can see over here, as I change the angle of incidence, the deviation also will change. The deviation also, how much does it deviate by also changes. Now, to better understand deviation, I will better rotate the prism because then it becomes very obvious. Rather than rotating this, I will rotate this. It's one and the same thing. I rotate the prism or I rotate the torch, one and the same thing. Okay. The ray was supposed to go like this. How much is it deviating by? See, earlier it deviated so much. Now it deviated less. Now more. Do you see that the deviation was maximum then, or a large value earlier? Then it became less. And then again it started increasing, which means for different angles of incidence, deviation is different. But for a particular angle of incidence, the deviation, see, now it is minimum. It is minimum because after this it increases. So over here, I think it was minimum. The deviation is the least here because after this it increases. So if one draws the graph of deviation with an angle of incidence, it looks something like this. Is it now making sense to all of you why it is looking like this? Why it is looking like this? It is becoming minimum for some particular angle over here. Watch it once more. Watch it once more. See, it is deviating by a large amount. Now the deviation decreased, minimum, and again became more. So that is why it decreased, and became more as the angle of incidence has changed. So when the deviation is minimum, as you can see, this is when it is probably minimum over here. Then a peculiar thing happens. I'm not sure whether you're able to see this very clearly. This angle and this angle, the incident angle and the emergent angle, both are going to be equal in amount. Both are going to be equal in amount. Correct. Yes, both are going to be equal in amount. And that is what happens. So when the deviation is minimum, when the deviation is minimum, then the incident angle is equal to the emergent angle, number one. Even R1 will be equal to R2. That is also second thing. That means the internal angles are also going to be equal. Everything is going to be symmetric. Symmetry will be there. Symmetry will be there on both sides. Even the ray inside will be parallel. Even the ray inside is parallel to the base. Can you see that? The ray inside is parallel to the base. Everything is symmetric. So the ray inside is parallel to the base of the prism. Is parallel to the base of the prism. Everything is going to be symmetric. And when that happens, that minimum deviation formula comes out as this. Mu is equal to sine of A plus delta minimum by 2 by sine of A by 2. Very crucial, important formula. Refractive index is sine of angle of prism plus delta by 2 by sine of angle of prism by 2. This is the formula. But if the angle of prism itself is very small, thin prism, this prism is large prism, big prism, big prism, big prism, big prism, thin prism, 2-3 degrees is the angle of prism. Then you can do some approximations, small angle approximations. So for thin prisms, very important, when you have a thin prism, then the deviation approximately becomes refractive index minus 1 into A. Very important. Refract mu minus 1 into A. Basically, this graph which is there, which is shown right over here, this is usually true for large values of A, angle of prism. But the moment you have a thin prism, you will see this particular graph just becomes like this. In fact, the deviation is not even going to be too much. It will not be so high also. It will be somewhere over here. So you will see this is how the graph will look like. The minimum deviation and any other deviation is approximately the same. Delta is approximately delta minimum is small and same throughout. What is this for? This is basically for thin prisms only. This is basically for thin prisms. It is not so curved. The curve becomes very flat. It is not much deviating for many angles. That is the difference when it is a thin prism. So that is something which you are supposed to know. Now, they are not given any questions over here, but if at all there was a question, how could it be framed? Let's say it is given to you. Let's say it is given to you, my dear students, that you have an equilateral prism, equilateral prism with a deviation of 30 degrees for incidence of 45, or let's say 40 degrees. Find the emergence angle. Find the emergence angle. How do we do this particular question? This is very straightforward question. First of all, let's see what and all is given. Equilateral prism. Equilateral prism means angle of prism is 60 degrees. Deviation clearly given to be 30 degrees. Incidence, that means I, is also given to be 40 degrees. Emergence angle, that is asked. Is there a relationship between all of them? Definitely there is. Remember, deviation is I plus E minus A. I plus E minus A, that is the formula. So delta is I plus E minus A. Therefore, E is equal to, or take E over here. So it will be delta minus I plus A. So what is the deviation? Deviation is 30. What is incident angle? That is 40. What is angle of prism? Well, that is basically 60. So 30 minus 40 minus 10. Minus 10 plus 60, that is going to be 50 degrees. So emergent angle is 50 degrees, as you can see. Is this going to be minimum deviation? No. This is not minimum deviation, as I is not equal to E. Emergent angle and incident angle are not equal, hence they are definitely not going to be minimum deviation. Let's say another example we have. And it says that you have an angle of prism given to be 30 degrees, and you have the deviation which is minimum, and that is also given to you. Let's say that is maybe 60 degrees. Question is, find refractive index, incident angle, emergent angle. Can you do this? Yep, definitely we can. We can definitely try doing this. First of all, to solve for refractive index, let's use this formula right over here. Refractive angle of prism is big, so for large angles use this formula, sine A plus delta by 2 by sine A by 2. This is the formula which has been given to you. Okay, so refractive index is sine of A plus the minimum deviation by 2 by sine of A by 2. Okay, sir. So what is the angle of prism? It is given to be 30 degrees. What is the minimum deviation? It is given to be 60 degrees. Whole thing divided by 2. Whole thing divided by sine of angle of prism. The angle of prism, that is basically 30. I think I had to make this opposite, not like this. I wanted this as 30, this as 60. That would be okay. Okay, so this will be then sine of A by 2. Angle of prism is basically 60, whole thing divided by 2. Yep, I just interchange the values, or else it will not be a standard thing. So therefore, the refractive index will be 30 plus 60, 90. 90 by 2, 45. So it will be sine of 45, whole thing divided by 60 by 2 is 30. So sine 30. What is sine 45? It is 1 by root 2. What is sine 30? It is 1 by 2. So this will be root 2 and 2 on the top. So it will be root 2. So the refractive index approximately is 1.414. So that is the first answer. Okay, job done, sir. What about I and E? How do we do that? Well, there is a simple thing. Delta is I plus E minus A, and these both will be equal if this one is minimum. Oh, perfect. So what is the minimum deviation? Already given 30 degrees. What is I and E? Equal. So 2I minus angle of prism 60 degrees. Okay. So shift it over there. So 30 degrees plus 60 degrees. is equal to 2 times of I. So 90 degrees is equal to 2 times of I. Therefore, I is nothing but 45 degrees. And E is also going to be 45 degrees. So incident angle and emergent angle both are 45 degrees. Got it? Yeah. Yes. Perfect. Perfect. Yeah. Cool. Clear. Shall we go ahead? Shall we go ahead? Yep. Great. Yes, Krishna, 45 degrees. Yes, 1.414, which is root 2. Yes. Oh, thank you also for reminding me to have some water. If they tell you there is a thin prism of 4 degrees having refractive index 1.5, find the deviation. How will you solve that question? Well, because the prism is thin, the deviation always is given by A into mu minus 1. That is the formula. If you forgot this, where it came? Right over here. A into mu minus 1. That's it. Just use it and directly you will get the answer. Angle of prism 4 degrees, mu 1.5 minus 1. 1.5 minus 1 is basically 0.5. 0.5 into 4, that's just 2 degrees. So the deviation is going to be 2 degrees. Such problems are very laddu problems or very simple problems. Then nothing is great in that thing. Okay, very, very straightforward questions. So I made you do some questions on prism. So now you know how to solve these questions as well. All right. Let's get to optical instruments, and this is the last part of this chapter. Direct questions may come in your NEET examination, and you don't even have to know the derivations as such. You just need to know the formula and the basic working, what is happening. That's it. Your job is done. So what's an optical instrument? An optical instrument is basically to see a bigger picture of the object. I am seeing through microscope a blood cell. I am seeing a tissue. I am seeing a plant cell. I'm trying to see mitochondria. I'm trying to see something else. I'm trying to analyze some sample. So I will use a microscope or I will use a magnifying glass. That's an optical instrument. You become an astronomer or you become a space you go into space or you become a space tourist or you want to see a distant mountain, so you use binoculars or you use a telescope. So that is also an optical instrument. You are seeing a faraway object in an enlarged manner. So basically it magnifies, it enlarges it, and the final outcome should be virtual in nature. Makes sense? Or else imagine you are using a telescope and you are getting a real image. So you need to buy a cloth and you have to put it somewhere and allow, oh sir, yes sir, I'm getting an image over here. I don't want to do that. I just want to see. Imagine you are using a binoculars and you are getting a real image. So you have to place the binoculars and then you have to hold the cloth. Oh, I'm getting an image over here. It will look stupid. Even imagine seeing a cell or a blood tissue or something on a cloth, on a real image. No. You want the image to be virtual, number one. Should it be erect or should it be inverted? I don't care really. Even if it is inverted, I'm okay with it. Just imagine I'm seeing a distant thing and let's say a moon or let's say a tissue. I get an inverted image. I'll be like, okay, fine. I will just look at it in the opposite way. I'm okay with it being inverted or it being erect. Both are fine with me. Next, it should be 100% magnified. That I can't compromise on. I don't want a diminished image. So that is what we are going to see. All right. Now there are, first of all, one main thing is there regarding something called as the magnification, magnifying power, which is way different than magnification. So let me define first what is the meaning of magnifying power. Magnifying power of an optical instrument. This magnifying power of an optical instrument is basically defined as the angle subtended by the image using the instrument. using the instrument, the whole thing divided by the angle subtended by the object without that instrument. What do I mean by this? Imagine this is the person observing a beautiful champa over here. Champa is very tall. So he is not using any optical instrument like telescope, microscope, anything, binoculars. So champa is subtending some angle over here. Let's say I call it theta naught. So this is basically theta naught, the angle subtended by this object without any optical instrument. But in the second scenario, what happens? This Pandu is using some kind of binoculars or something, I don't know, some optical instrument he is using. Okay, so because of which, what happens is this particular Pandu sees a image of Champa maybe like this. Then this will be the angle subtended by the image. It's not actually the object. This was the object. This is actually the image because of that optical instrument, maybe a spectacle, whatever. So that is basically your theta prime or theta 1 or whatever you want to call it. Theta prime, theta 1, theta, anything that you want to call. So this by this is called as the magnifying power. It's a ratio, it's unitless, dimensionless. It is not the same as magnification. Note, it is not the same as magnification. Magnification. Is this clear? It's not the same as magnification. Is this absolutely clear? What is the meaning of magnifying power? So you might have seen on the microscope, it would be written 10x, 50x, 80x, 300x. What is that 300x, 80x? Magnifying power. So if there is a tissue of 1 millimeter, because of that microscope, it will look 300 times bigger. That means 300 millimeters. That's quite large. Got it? So that is the meaning of the word magnifying power. How many times angle wise does it get expanded? Awesome. Now there are three instruments. One is the simple microscope. Then you have the compound microscope. And the last one you have the telescope. Let me explain this to you via simple diagrams right over here. Why not? What exactly might be happening? So let's say a beam of light, and let's use a simple convex lens over here. Oh, not this one. Observe this now. This is a convex lens. We know the rays will converge. For a concave, it diverges. Obviously, using a concave lens is meaningless because if there is an object over here, imagine there is a penguin. I will see a smaller picture of the penguin. I don't want that. I want a bigger picture. So definitely, I will not use a concave lens. I will use a convex lens. But I don't want the image to be real because this side it is real in nature. So what I will do, I will make sure this is my magnifying glass. I am seeing through a magnifying glass. I am seeing this object. I will go closer to the object, or I will bring the object closer till it comes before the focus, not beyond, but before the focus. The moment I go before the focus, a very interesting thing happens. You can see that the image becomes virtual, it becomes enlarged. and it is also erect. That is a good advantage only for me. So I can see an enlarged image of that particular object. Are you able to see? So this is the functioning of a magnifying glass. The same diagram, but in a very boring way, has been mentioned over here. See this? This is an object, this is the image. It's virtual in nature. Can you see that? Virtual image, real object. Yep. Object, virtual image. Is this clear? But I have two options with me. Now, you might have heard about this human eye since you are biology students, that human eye is a very miraculous lens and it has got the power of accommodation. Means it can adjust its focal length, everything, depending on what are you concentrating on. If you are seeing a distant mountain, the things, the ciliary muscles will contract, expand, etc. and it will focus onto the distant mountain. I am seeing something very close, it will again focus itself on that closer object. But there is a limit till which it can accommodate depending on how well your eye is maintained. So one is called as the near point, the other is called as the far point. Near point is the closest distance till which your eyes can strain your ciliary muscles and can focus. I can see my hand now. I can see it now. Now I'm not able to focus. Now I'm not able to focus. It's looking blurred. So there is a near point, and usually for an average human being, it is 25 centimeters. Because whenever you want to see things clearly, what will you do? You will go close, right? You will not go, sir, I want to examine this sample. Push it far away. You are stupid then. If I want to examine a sample, you will bring it close. But you can't bring it too close. You will be like, okay, sir, I put it on my eye, sir. I can't see, sir. What is happening, sir? It's too close. Obviously, you have to place it at the near point. And your near point is 25 centimeters for an average adult. Correct? Got it? Similarly, the far point is usually infinity, means you can see a star. How far is a star? Infinitely far away. So you can see stars, that means your far point is infinity. But if you have a defective eye, then the far point can be 10 meters or 2 meters. There are some people, I can't see what teacher is writing on the board. That means the far point is not infinity, he has a defective eye. That can be corrected using lenses. Same thing can be corrected for a near point defect as well. Okay, fine. Now, if I want to see this penguin's image clearly, what will you do? Will you keep the penguin at the near point, or will you keep the penguin really far away? See, if you keep the penguin really far away, yeah, well, I have to focus. My eyes are a little less trained, okay, but it is far. Whereas if I keep it from my eyes, this is where my eye will be, this is where the magnifying glass will be, at 25 centimeters, very close, and I will see a big image. So I will try to keep it at the near point to get a very crisp, crystal clear image, magnified image as much as possible. So that kind of setup where the image is formed at the least distance of distinct, that means clear vision. That is one setup. And the other setup is when I place the object such that the image is formed really far away point. The image is very, very far away. My eyes will be relaxed. When I see far away, some sunset I see, I'm relaxed. But I'm seeing some point on my nail, 5 hours. I will lose my mind. Yeah, because my eyes will be strained. Got it? So that is what the two arrangements are. Is this clear? Distinct vision, least distance of distinct vision arrangement where the image is at 25 centimeters approximately. That is called least distance of distinct vision arrangement. This one, when it is really, really far the image, that is usually called as normal vision. Normally, when you are seeing things are far away. So normal vision, your eyes are relaxed, at peace. So that it is normal vision. So in both the cases, the magnifying power has been defined. So let's have a look at the formulas as it is. You don't need the derivation. So the magnifying power is 1 plus d by f, where what is the d? What is the d? This is basically your d, my dear warriors. 25 centimeters or more. What is this? 25 centimeters is 25 centimeters given somewhere. No. So D is your least distance of distinct vision, which is approximately 25 centimeters for an average adult. It could be different for many of you. If you have a defective eye, it might be more. If it is very good, it might be even less. Okay. So that is your D. What is F? F is the focal length of that lens. So it is 1 plus D by F. This is for LDDV arrangement. This is when the image is at the near point, that is least distance of distinct vision. But if at all you decide to keep it very, very far away, this is your normal vision. Normal vision. That means the image is at infinity. The image is at infinity. So you can see it is D by F. No 1 plus D by F, it is just D by F. Is this clear? These are the two magnifying power formulas. Remember, magnifying power, I had defined this. So magnifying formula, when you are close, it is 1 plus D by F. When it is very, very far, then it is just D by F. These are the two things that you need to remember. Okay. Now, I'm not very satisfied with this. Let's say, for example, if I use, say, a microscope, simple microscope of focal length 5 centimeter, what is the max and minimum magnifying power? What is the maximum and minimum magnifying power of that simple magnifying glass? The answer will be the magnifying power for normal vision, which is just D by F, D being 25, F being 5, will be 5x or 5 times. The magnifying power for least distance of distinct vision will be 1 plus D by F, which will be 1 plus 25 by 5, which is 1 plus 5, which is 6. So this is obviously the maximum, and this is basically the minimum. So when you're holding it very close, it is 6 times magnified. When you're holding it very far, normal vision, it is 5 times magnified. But this might not be enough for most of the cases. 5, 6 is a very small number of magnifying power. We need more values. So you will be like, let's use more lenses. And that is exactly what is done for a microscope. So this is basically the diagram for a compound microscope, which uses two lenses. And the diagram is shown as here. The produces the final image which is enlarged as well as virtual. The first image is inverted. Okay, the final image is inverted with respect to the original object. Okay, so this is your basically compound microscope. Now let me see if I can somehow make that compound microscope for you. It's slightly difficult. This is a convex lens. I need one more convex lens. No, I can't do it over here. Sorry guys, I can't create that over here as of now. It's not allowing me. I can't create two lenses. I wish I was able to add two lenses. Then I would have been able to show it to you. Okay, anyways, I'll just show you here only what exactly is done. There is a lens here, and there is an object which is placed. The rays from this particular object, the rays from this particular object, let's say they will go like this. Okay, they're going like this. So they are meeting over here. So definitely an inverted image is formed right over here. Definitely an inverted real and enlarged image is formed right over here because of this lens. Now you use one more lens right over here. Now you use one more lens right over here. This lens is such that this point or this image is before the focal length of this lens. By the way, this lens is also called as the objective lens. Reason being it is closer to the object. This lens is also called as the eyepiece lens or just the eyepiece because your eye is where the lens is. Yeah, and it's closer to the eye. That's why eyepiece. You see through that lens because the focal point of this lens is here, and the object, which is actually the previous guy's image, is before the focus. It will now make an enlarged image because of that. So you will probably see things going like this. Mhm. 1 second. Now I have to extend it backwards because it is virtual in nature. It is meeting over here. So I will see that the final image is formed somewhere over here. This is the final image. Whatever I showed over here was an intermediate image. This is the final image. Now this final image, as you can see, if it was here, it is below. So it is definitely again inverted. But you had to extend the rays. That means it is virtual in nature. And lastly, it is enlarged. So this is a two-stage magnification. First time it gets magnified here. Second time it gets magnified here. So you get multiple magnifications. So because of which you get a finally, a big image right over here. I hope this is clear. I hope this is clear. Yes. Shall we go ahead? Shall we go ahead? Harry, first of all, I know your institute and I know how these kind of institutes work and trying to spam onto different channels. I know you guys have even gone to some big popular channels also and spam. So really, I don't care. Thank you so much. Don't spam. I'm just going to block you. Okay. Right. So moving on to the formula for the magnification. 1 second. Oops, I don't need to delete this. Yeah, this and this not needed. Okay. Right over here. Yeah, so the magnification formula that you get, yes, is right over here. So let me just write it over here. The total magnification is this one right over here, where what are these terms? D is your least distance of distinct vision, which is 25 centimeters for an average adult. F naught and Fe. F naught and Fe are basically the focal lengths of objective and eyepiece. FO is the focal length of objective. Fe is the focal length of the eyepiece. Lastly, you need something called as the distance between the two lenses, which is L. This is also called as the length of the tube, length of the tube of the microscope. So that is basically your L. So the magnification is given by, magnifying power is given by length of the tube by focal length of the objective. Objective is basically this guy, L by FO multiplied by D by FE. What is D by FE? Least distance of distinct vision divided by FE. That's it. That is what it is. Very good. All right. And Bhargavan, let me also tell you that there are reasons for that, because I got spammers on some videos. You know, see, these are the cheap tricks used by some of the teachers. And unfortunately, some good teachers also fall to this prey because of certain institutes. I don't know whether the teacher was involved or not, but some teachers or maybe some institutes use some cheap tricks going on to videos when you have left a channel, going to that particular video and commenting on every comment, saying that, hey, you know what, I'm here now, you can watch this. Hey, you know what, I'm in this, I'm doing that. So these are the kind of tricks and stupid things which many people do, which is why, and they were not real students. I know real students, genuine students never do that. From some fake accounts create, comment replies and, suggesting students, hey, don't watch that, and spamming onto the existing teacher's class saying that, hey, this teacher is not teaching well. Hey, this teacher is not doing that. Hey, teacher is not doing this. This is what I don't like. Otherwise, we never do such things. We never had to make things private. So really, those students who actually comment such things on such videos, they are not even, first of all, real students. Number two, they are probably influenced by the institute or by the teacher. So really, I don't care about such people because they are not genuine students. I really only care about students. That's all. Only care about students. For me, what other teachers say, what they don't say, I really don't care, honestly. For me, students' lives matter. Okay. Moving on to the question, moving on to the next concept right over here. So magnifying power, yes, this is done. So they have just given an example. Imagine a microscope whose objective of the focal length has 1 centimeter focal length, and the eyepiece has a focal length of 2 centimeter. The length of the tube is 20 centimeters. Then what do? Length of the tube by FO, D by FE. Length of the tube is 20. Focal length of the objective 1. Then eyepiece has a focal length of 2 centimeters. D is 25. They have substituted. You can see this is a huge magnifying power, which is 250 times. If you compare it with our previous example of a simple microscope 5 and 6, that was very nominal. So my dear students, this is much, much larger. Much, much larger. I hope this is clear. Yep. Very good. Awesomeness. Moving on to the last instrument, and that is the telescope. It is also very much similar to a microscope, just one small difference is there. I will tell you what the difference is. Imagine again, this is our objective focal lens. This is our objective lens. It's just that our object won't be very close. Unlike over here, it will be very, very far away. Like you will be seeing a moon, a mountain, or a star or some galaxy. It's very, very far. So it's a very far away object, very far away object. And this particular very, very far away object will make an image right over here. When the object is very far, the image is formed at the focus. So this is an intermediate image, which is going to be real inverted, which is going to be real and inverted. Then you take another lens over here, which is obviously your eyepiece, and you ensure that the final image which is formed, this is your final image which is formed is going to be inverted, it is going to be virtual, very similar ray diagram to the microscope, just that the object is very far, and it is what else is there? It is highly enlarged. It is definitely going to be enlarged. So this is what happens for a telescope, just that the object is really far, and this is where your eye is. Now again, same thing. This is the length of the tube, length of the tube of the telescope, length of the tube of the telescope. Perfect. This is basically the length of the tube of the telescope. Number two, basically, you know, this is the focal length of the objective, focal length of the objective, right? Basically, reason being, when you have a very far away object, the rays will converge close to the focus. So that's why this becomes the focal length of the objective. This image is very close to the focal point of the eyepiece also, because of which the image gets highly enlarged. I'll tell you why. Just look at this. Just look at this. Imagine a very far away object. See, if you have a very far away object, if you have a very far away object, see what is happening. The image is formed very close to the focus. And if the object is close to the focus, the image is highly enlarged. I hope you can see the image right over here. It is highly enlarged. So, if the object is close to the focus, the image is highly enlarged. And if the object is very far, the image is formed very close to the focus. So this characteristics is what we have used. Object is far, the image is formed at the focus, and the image becomes the object for the next lens. So if the object is very close to the focus, that means this becomes approximately the focal length of the eyepiece. Then the image is highly enlarged, and that is what exactly you want. So that is the reason why you will see that the length of the tube is FO plus FE in most of the telescopes, and that is what also would have been mentioned over here. Yes, as you can see, the length of the telescope is F naught plus FE. Can you see that? The length of the tube is F naught plus FE. So that is one thing. Last thing, the magnifying power is FO by FE. The magnifying power of a telescope is focal length of the objective by focal length of the eyepiece, which has just been mentioned right over here. That is something which you should again remember. Okay, so say for example, if you have an objective focal length of 25 centimeter, or let's say 50 centimeters, eyepiece has a focal length of just, let's say, 0.5 centimeter. So 50 divided by 0.5, 5 cancels, it will become 100 times. So the magnifying power will be 100x. So you will see a very good clear image because it has got 100 times the magnifying power. That's how you calculate the magnifying power of the telescope. Okay, so that is what they have mentioned. And the last paragraph, they also tell about some additional things about the telescope, regarding some considerations. You will see that the objective of a telescope, if you see a telescope, if we just even Google the image of a telescope, okay, let's say even just we see how a telescope looks like. Yep, look at this. Big objective, small eyepiece. Big objective, small eyepiece. Yes, can you see? Big objective, small eyepiece. Can you see that? See, the objective is so big, the eyepiece will be very, very small. The objective is very, very big. Can you see that? Objective is very big, the eyepiece is very small. Why the objective is very big? Why is the object big? Because when you see distant stars, moons, planets, galaxies, anything, celestial bodies, the light coming from them is very small. Now, we know this fact. If more light falls onto the lens, the image formed will be more clear. That's the reason why the diameter of the objective, is very big, so it can take in more and more light to make a very clear image. Number one. Number two, Number two, the number two fact is that there is a phenomena called as a diffraction, which is deleted right now from the syllabus, which states that when you have a small hole, then the light which enters it spreads. Now that is an undesirable effect. Imagine the light is passing through a very small diameter, then it will spread, and the moment it spreads, it's going to cause undesirable effects. That's the reason why if you have a big diameter, then the light will converge very clearly, the image will be resolved properly, the image will be crisp, and the undesirable effects of diffraction are no longer there. So that is why they have mentioned that the diameters are very large. With large diameters, even the fainter objects can be observed. The resolving power or the ability to observe two objects distinctly, which are nearly in the same direction, also depends on the diameter of the objective. So that is the reason why you make the diameters very, very large. That is what has been mentioned over here. In more advanced telescope, they also use mirrors and other things. Modern telescopes, they use concave mirrors rather than a lens for the objective, and these type of telescopes, they are called as reflecting telescopes. That particular thing is not there in our syllabus. So the telescope images which I just showed it to you right over here, they need not have two lenses. Sometimes they even have mirrors, they even have prisms. So combination of even more lenses can happen. So those are modern day telescopes. Okay, that is something which has been mentioned. Chumma they are told. Okay, they are like showing off. Hey, listen, modern day, many lenses are there. Hey, I'm not going to teach you. Hey, listen, there are mirrors also, but you are not going to study. So some show off has happened in this last paragraph, and they end it over here. So to summarize this particular chapter, we started off with reflection, which was angle of incidence is angle of reflection. Then we went to refraction, which is the bending of light. We saw Snell's law, which is sin I by sin R is refractive index, which is the ratio of the speed of lights. Then we saw a critical angle phenomena. When light goes from dense to rare, it bends away from the normal. So you have a limit on the angle of incidence called as the critical angle. Beyond that angle, the light internally reflects. Then we saw the mirror equation, which was 1 by v plus 1 by u is 1 by f. Focal length of a concave or convex mirror is r by 2. We also saw the sign conventions. Then we also saw lens formula, which was exactly same, just you have a minus sign. But the focal length given by the lens maker formula, which is mu minus 1, 1 by r1 minus 1 by r2. We also saw prisms and how deviation depends on the incident angle. The formula for deviation, which was I plus E minus A, R1 plus R2 is A, and for minimum deviation, it is sine A plus delta by 2 by sine A by 2. We also saw thin prisms. We also saw combination of lenses where the powers get added or the reciprocals of the focal lengths do get added, right? And finally, we ended the lecture with magnifying power, which is the angle subtended because of the instrument upon angle subtended by the object without the instrument. So the ratio of magnifying angles. Yes. And we saw for basically a single lens, it is 1 plus d by f or d by f, depending on whether you are holding it close or far away. For a microscope, L by f naught into d by fe. For a telescope, just f naught by fe. That is what we have seen. Dispersion is not there in NCERT, but they have just mentioned that dispersion is splitting of light. I can just show you what dispersion is right over here. Just let's get rid of this. Just imagine I take this prism, and instead of this, what if I use white light? Wow, it looks so nice, guys. I hope you can see. This white light has been, I don't know whether you can see it, it has been split into its constituent colors. Violet, indigo, blue, green, yellow, orange, red. Violet deflecting the most, red deflecting the least. This also means every color or every wavelength has its own unique refractive index. Violet having the highest refractive index because you can see violet has been deflected the most. Red having the least refractive index, that means it is deviated the least. It also shows that if you mix all these colors of Vibgyor, violet, indigos, blues, yellows, oranges, reds together, you see or perceive, the human brain perceives it as white color. So white is a mixture of all these colors together. And the best thing is I can also add multiple more prisms over here so that I can even spread it more. I hope you can see more and more refraction happening as we progress. Yeah, see, more and more refraction is happening as we progress, and more dispersion. Dispersion is basically where you split the light and we figure out what is it made of, why it is made of all these colors. So that is basically dispersion. It's nothing but, splitting of light into its constituent colors. Awesome, right? So that is what it has been mentioned. So that's about it, and we are done. Now, in the introductory part of the wave optics, it talks about the different theories of light, starting off with almost 400 years back when Newton gave his theory where he believed light was particle, and he said the different colors that we see is because the different sizes of these particles. He called these particles as corpuscles. That's why it is also famously called as the Newton's corpuscular theory. And he also said that because these particles, when they enter into a dense medium, they slow down because they have some, size and all of that. So he explained why the speed of light changes when the medium changes. But, there was another person called as Huygens back in the 1600s, who was again a famous Dutch physicist, who said, no, light is not a particle. And he said that refraction, reflection, these phenomena can't be explained by particle nature of light, rather wave nature of light. And he also showed some experiments and all of that. But Newton being the more dominant guy, people did not believe whatever Huygens said, and his theory was discarded. Although Huygens' theory was actually very interesting, and that is what we are going to study even after 400 years. Even though there were some flaws in it, it has a very natural flow in it. It gives you a proper feeling of how refraction and reflection might be working, and so many other explanations which occur very naturally. Other people like Foucault, Snell, and so many others, Young's, they all went against Newton and said that, light is not particle. What you are saying it is a corpuscle is not right, rather it is a wave. All of them kept shouting, but nobody believed them until Maxwell arrived after almost 200-300 years, and he gave the electromagnetic wave theory of light. And that's when people understood, okay, wait, light is actually an electromagnetic wave. And he was able to explain all the other phenomena which light exhibits. So there is a separate dedicated chapter in physics. We know electromagnetic waves. So here the few things like the corpuscular model of light, okay, which was given by basically Isaac Newton. And he also predicted that it bends towards the normal, then the speed of light will be greater in the second medium, but which was again contradictory. And then came Huygens principle. Huygens principle put forward the wave theory of light, but the wave theory was not accepted because Newton's dominance and light could travel through vacuum, and it was felt that wave would always require a medium to propagate from one point to other. There were some things over there which we'll be talking in a bit. Huygens theory of light. Finally, it was understood that light is actually an electromagnetic wave. So Maxwell put forward his electromagnetic wave theory, and he developed a set of equations. We have seen that, and that's why we know light is basically an electromagnetic wave. And he was able to calculate the speed and explained very different phenomena regarding light. So that is basically there in the theory part initially in the introduction, but mainly we are going to focus on the Huygens principle. So what exactly is this Huygens principle? What did he assume, and why was it even not considered, and why is it even considered? All these things we are going to see. Hi Thanos, hi Mardi. Welcome aboard all the warrior Pandus. Nice to see you all back. Yeah, welcome. Thank you for warming up the chat box early morning. So, Huygens said that, first of all, he defined a wavefront. So, he's basically when you drop a stone, the wave spread, every point on the surface starts oscillating at some instant. If you take a photograph, shows circular rings. Clearly all the points on such a circle are oscillating in the same phase because they are in the same distance, such a locus of the point. So let's start defining what is a wavefront. So let's define a wavefront. So they start oscillating in phase. Such a locus of points which oscillate in phase is called as a wavefront. Thus a wavefront is defined as a surface of constant phase. The speed, the next important point over here, the speed with which the wavefront moves from the source is called as the speed of the wave. The energy of the wave travels in a direction perpendicular to the wavefront. Okay, now if you have a point source emitting waves uniformly in all the directions, then the locus of the points which have the same amplitude and vibrate in the same phase are spheres. Hence we have something called as a spherical wave. Okay, so here they tell that if you have a point source, then you have basically spherical wave, because all the points locus which will oscillate together will be in terms of sphere. So a small portion of that particular sphere can be considered as a plane wave and what we know as a plane wavefront. Let me explain this to you with a simple idea. See what they tell. A wave is nothing but a disturbance which moves in the medium, or disturbance which propagates around you. When you talk, there is a disturbance, and that disturbance moves everywhere. So to explain that, imagine there is a drop of water which falls on a pond or a lake. The disturbance will move everywhere, and you can see it from the side view. It's very easily seen. See, this drop of water falls. You can see this disturbance is moving everywhere throughout the pond. Now this is the side view. If I see it from the top, then you will see how the disturbance goes here, 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 everywhere. So the locus of all the points which have the same oscillation is called as a wavefront. So right now, as you can see, this particular thing is a wavefront. The wavefront is growing in size. The direction in which the wavefront goes is called as the ray. And in that same direction, and it's exactly in the same direction that the energy of the wave travels. So the energy of the wave is traveling exactly perpendicular. This is the wavefront, perpendicular to the wavefront. So that is what has been explained in the first few lines over here. The locus of the points which oscillate in the same phase is called as the wavefront. The speed with which they travel is the speed of the wave, and the energy of the wave is always perpendicular to the wavefront. So if this is the wavefront, it is always perpendicular, and the speed with which the wavefront moves is also the speed of the wave. So if sound is there, the speed at which the sound wave travels is also the speed with which the wavefront of the sound travels. You can see this is the speaker. So it is basically vibrating. So it is generating some sound. So the speed with which the wavefront of the sound travels is also basically the speed of the sound wave, which we know is around 340 meters per second. For light, it is around 3 lakh kilometers per second. Okay, so it's a huge distance. Now basically, if you have, just imagine this. If you have a point source, what will happen? It will create a disturbance around it. It will definitely create a disturbance around it. And after some time, the disturbance will reach here like this in all the possible directions, up, down, front, back, left, right, and it will look like a sphere. But that sphere will keep growing in size. And it will look something like this. And these are nothing but spherical wavefronts. This is nothing but your spherical wave front. This is nothing but your spherical wavefront. The direction in which the wavefront moves, like this one, these will be called as the rays of the wave. The rays of the wave, like rays of light, rays of sound. So it is the rays of that particular wave. These rays are always perpendicular, and also notice it's the same direction in which the energy will travel. The energy travels exactly in this particular direction. Also, the speed with which the wavefront moves is basically the speed of the wave. The speed of that particular wave, which we have already seen, is the frequency times the wavelength, which is nothing but frequency times the wavelength. Hi Rajan, hi Charanya, welcome aboard. Now, when you go really far from such, spherical wavefronts, just imagine you have gone really far. Okay, just imagine I draw one more spherical wavefront. I go really far from it. Just imagine this, something like this. When you are really far from such a particular wavefront, source, our source is here, and you are really far away, this particular spherical wavefront, which is there, it loses its curvature. As you can see over here, if you just consider a small part of it, it looks as if it is a plane. So it looks like a planar waves front. It looks like a planar wavefront. And a planar wavefront just probably going like this. You won't see much of a difference between the rays of light, although they are diverging in nature, but it will feel as if the rays are approximately parallel to each other. You will feel as if the rays are parallel to each other. So if you had to see it more clearly in 3 dimension, it will look something maybe like this. So just imagine this particular wavefront. Something like this, and the rays of light are going like this. So these are the rays. Are you able to visualize this? So these are the planar wavefronts. Yes, they look almost parallel to each other when you are really far away from a large spherical or from a source, and the spherical wavefront becomes very large. So the curvature loses out and you feel almost like a plane. Is this absolutely clear? Madhumati, Rajan, Charanya, everyone with me on this? What has been explained in the first few lines of this particular NCERT paragraph? At large distance from the source, the small portion of the sphere can be considered as a plane, which we call as a planar wavefront, which they have shown here. So this is a point source, how it is generating spherical wavefronts, and when you go really far away, it becomes a almost planar wavefront. Okay. Now, once we understand what a wavefront is, then come back to Huygens theory. It allows us to determine the shape of the wavefront at a later time. Thus, Huygens principle is essentially a geometrical construction. And this is very important. So what Huygens idea is basically to allow us to determine the shape of the wavefront after any time. So basically, the principle is nothing but a construction method which gives me the shape of how the wave will look after any time, so that we understand how it will look, where it is, what is the shape, what's the size, and all of that. So what is the theory? According to the theory, each point, according to Huygens theory, according to Huygens principle, each point of the wavefront is a new source, which is called as a secondary source or a secondary disturbance, and it creates secondary waves from these points which spread out in all the directions with the speed of the wave. These secondary waves emitting from the wavefront are usually referred to as secondary wavelets, and if we draw a common tangent to all these spheres, we obtain the new position of the wavefront at some later time. So if you want to determine the shape of the wavefront, we draw spheres of radius. We draw spheres of radius v tau. This is at time tau. And here v represents the speed of the wave in that particular medium. Then you draw a common tangent to all the spheres. We obtain the new wavefront at time tau. In this particular model, there is a particular catch. I will explain all these things. For now, I am just underlining it. We also have a back wave which is also shown, but Huygens argued that the amplitude of the secondary wavelengths is maximum in the forward direction and zero in the backward direction. By making this random assumption, Huygens could explain the absence of back wave. However, this assumption is not satisfactory, and the absence of back wave is really justified from a more complex model of wave theory. In a similar manner, we can also use to determine the wave for different mediums. Now, what he is trying to say in these lines over here, let me tell you. First of all, Huygens believed that whenever you create a disturbance, then that disturbance is basically called as the source. The disturbance is basically called as the source. Now, when I say disturbance, that means it is nothing but energy. So basically, the energy which is being created, that energy begins to flow, and that energy flows in a medium. Now, he said that light travels in a medium called as ether. The medium of light was called ether, and it basically keeps on propagating till it reaches its destination in all directions, you can say, all directions. So there are rays of light, and then there are wavefronts and all of that. Huygens argued that whenever you are seeing a light bulb, a candle, or some spark, some light coming, it is a disturbance in the medium, and that disturbance has some energy which is now flowing, and it is flowing in a medium called as ether. So he said light needs a medium also. It is there in the introductory part about this. But people went mad over this. They spent hundreds of years because Huygens said light travels in a medium, but nobody was able to find such a medium. So that is why Huygens' theory was also even discarded for that reason, because he said light needs a medium, but actually we know light can even travel in vacuum. He even argued that okay, even in vacuum there is something called as ether, but no such ether was ever to be found nor discovered. So understand that this is one assumption which he made, but actually it is not true. So as per Huygens, if you see, light is a mechanical wave. As per Huygens, light is a mechanical wave that travels in ether. It is not that organic compound ether which you are thinking about. Please remember, this is not true. It is actually a false thing. It is not actually true, but this was his assumption. Please remember that. Now he says that, one second. Now he says that, okay, fair enough. If this is light is a mechanical wave, let's say there is a source which has created a disturbance, and then because of that there was a wavefront which was created. So this was a wave front which was basically created. Now what he says is that each point on this particular wavefront, there are infinite such points, so I am just showing a few of these points. Each point on this wavefront, it will act like it will act like a new source, but this source is not the original source, so I will call it as the secondary source. Each point will act like the secondary source. Now when they act like a secondary source, what they will do is they will generate waves. Because of each of these sources. So each of them will now generate waves like this, secondary waves like this, each of them. So they are generating this called as the secondary waves. These are called as the secondary waves. Now why they are generating secondary waves here, and why not over here, and why not over here? Why not in the backward direction? So these would be basically secondary waves in the backward direction. Secondary waves in the backward direction. Actually, the light, whatever is there, it is traveling like this. Why these waves, these secondary waves in the backward direction are not generated? This was made as an assumption. He just said no, it is not generated for some reason. He just chumma made that assumption. He did not give any very concrete answer for that. He just said that if light is propagating in this direction, so obviously the waves which will be generated secondary will also be generated in that same direction in which it is actually it will be generated in the same direction in which it is actually propagating. It is propagating over here, so it will generate waves only in this particular direction, not in this direction. So that is what has been even mentioned over here, that the back wave is not made, and he made an ad hoc, that means on the spot assumption, but actually there is a very complex reason which we cannot discuss here, because of which the back waves are actually not generated. So there is actually a reason, but Huygens did not know it at that point of time, rather he was not able to think about it. So he chumma made one assumption, okay, but there is actually a complex reason for it, why these waves are not generated. So only the forward waves are generated. Now these secondary waves will interfere with each other, and you will see that the new wave after some time can be found by drawing a common tangent to all of them. Drawing basically a common tangent to basically all these waves. So this then becomes the new wave after some time, let's say tau. This is the new wave after some time, let's say tau. Now how do I know this is that same time tau? There is a way in which you can ensure it. See, when you are having this original wavefront, and you are considering these small secondary sources which are derived, these are not the original, these are secondary sources, and then you are drawing these secondary wavefronts, ensure that whatever secondary wavefronts you are drawing, their radius, the radius of the secondary waves is basically the speed of light multiplied by the time after which you want to draw it. Speed into time gives me basically the distance. Speed into time basically gives me the distance traveled by the wave in some time. So ensure that all these secondary waves that you are showing, their radius is just velocity of the wave into time, tau. So then I will be sure that this gap between these two wavefronts is exactly speed into time, which is the distance between the two waves, or the distance traveled by the wavefront. Is this clear? I hope this is absolutely understood. Electrostatics and capacitance already taught in the NCERT line by line series. Squeaky Cook. Okay, Namaste Swati. Welcome aboard everyone. Okay. Is this understood? Now, using this theory, you can construct the waves for any particular shape also. Say for example, I have been given a random wavefront like this. This is a wavefront which was given to me. I can find how the wavefront will look like after some time by just considering small secondary sources. These are our secondary sources. Then once I have the secondary sources, I will just show the secondary wavefronts, that's it. These will be the secondary wavefronts whose radius, the radius should be how much? The radius should be basically velocity into the time. Then the last step will be to draw a common tangent to all of them. Just draw a common tangent to all of them. So this is the new wavefront. This is the new wavefront after some time. After that time, which is basically tau. Got it? So even after some more time you want to draw how the new wavefront will look like, no issues. Again you take, basically you take small secondary sources. Again you show the new secondary wavefronts like this. Again you show the new secondary wavefronts like this. And again you draw the common tangent to all of them. So this is the more newer, I would say, wavefront. So you can keep drawing newer and newer wavefronts and see how the wave propagates with time. Very good. Now, based on this principle, you can explain the concept of refraction, and you can also explain the concept of reflection. So for that, what they do is basically they take an incident plane wave and see how it refracts. And then they also take an incident plane wave and make it fall on a reflector and see how it reflects. There was an animation, if I'm not wrong, which I've seen. Just a second. Let me see if I can find it. Okay. Through this is better. See, basically this is a very good example to see this. Observe this now. Okay, so light is coming from this torch as a plane wave. It will fall over here, it will refract and it will reflect. See how it looks like when it comes as a wave. See, these are planar waves, plane wavefronts. Can you see each of these lines are plane wavefronts? They are coming over here, they are bending, and it is also getting reflected. So this is exactly what we are studying over here. This is exactly what we are going to study, and very easily seen over here. Now observe one thing, forget the reflection part. Forget the reflection part for now. Just look at refraction. You take any plane wavefront, the lower part, the upper part, the middle part. As it moves, the first part which interferes or touches the medium is the lower part. The upper part of that wavefront has not yet touched the medium. So as soon as the lower part touches, it becomes slower. It becomes slower. It slows down. And as the wavefront progresses, as you can see, slowly one part starts touching the medium and it slows down. But the wavefront which had touched earlier, the lower part of it, had slowed down long time back. The upper part slows down after some time when that part reaches this particular medium. So you will see that the wave would have bent by some amount. Okay, try to understand again. This wavefront reaches here, this part slows down, so it has lesser speed. This is still continuing with the same speed. When it reaches here, then it slows down, but because this lower part had slowed down earlier, you will see that the wave has bent. It's like throwing a pen like this and it enters a rough surface, so this part, lower part of the pen slows down, this part is still fast, so it turns and then it goes down like this. Are you able to visualize? This was going on a smooth floor. This was going on a smooth floor. Now the moment it enters this medium, this part becomes slower, so you can see the pen turns and then finally it goes down like this. Now is it understood? Neha, maybe for 2 hours or so, who knows? So exactly that is what has been done over here in this entire derivation. So let me explain this to you in a very simple way. If I show you the NCERT slide, you might not really understand it so well. See, this is the surface interface, okay, and then you have the plane wavefront. Okay, so this is your incident wavefront. This is your incident wavefront. So what happens is the ray of light will come like this. Here also it will come like this. Right now it has reached till here. This is the first part which touches this particular medium. So immediately after that, what will happen? This part will slow down. This part will continue moving with the same speed. It has no obligation as such. This part will continue moving with the same speed. It has no obligation. But here what happens is, this part at this point it will generate a secondary wave. Are you able to visualize it? It will start generating basically a secondary wave, but at a much slower speed. The speed will not be much. It will start generating a secondary wave at a much slower speed. Meanwhile, this wave is still propagating ahead. Okay. Next step, let's see what exactly happens. This wave would have gone even further. You will see probably it would have reached here, maybe something like this. Okay, it has probably reached till here. Meanwhile, this point which just touched the medium over here, it will start generating a secondary wave. This secondary wave which was generated before would have by now grown a little bit in size. Would have grown now a little bit in size. The next instant, think about it, the entire incident wavefront would finally reach the medium. In fact, the last part also reaches here. Meanwhile, this point which just touched this medium before would have generated a secondary wave here. This secondary wave would have now grown in size like this. This secondary wave would have grown furthermore like this. And now at this moment it has just started to behave like a secondary source. It will generate secondary waves after this. So as a whole, if you notice what exactly has happened, my dear students, okay, observe this now. This particular primary wave eventually reaches here. Meanwhile, you will see that this point will behave like a secondary source. It starts generating secondary waves like this. Okay, that secondary wave, by the time this guy reaches here, has really grown in size. This, when it reaches here, it would have made a secondary wave, secondary wave, secondary wave, secondary wave, secondary wave, like this. This is how the secondary waves would have been generated over a long period of time by the time this point reaches here. Is this absolutely clear how this happened? Again, look at it. This point generates a secondary wave behaving like a secondary source. Then this point will behave like a secondary wave source generating a secondary wave. This would have grown by that time. This will further grow. This will grow. Now this will generate a secondary wave. Now this will generate. So basically you will see these secondary waves, but they are being propagated at a slower speed. They are being propagated at a slower speed. So if you draw a common tangent to all of them, if you draw basically a common tangent to all of them, if you draw a common tangent to all of them, this is basically my new, I would say, refracted wavefront. This is my new refracted wavefront. And this refracted wavefront will continue propagating like this. It will continue propagating like this in this particular direction. It will continue propagating like this in this particular direction. You can see that. So you can see the light has slightly bent because these wavefronts were slow moving. They were slow moving waves. So you can see the bending action of light, hence the light has just got refracted. Okay, so basically that derivation goes something like this, where you show this. Okay, you can start marking some points, like this point I can call it A, this point I can call it B, this point over here I can call it C, this point over here I can call it D. I can also draw perpendiculars. I can also draw perpendiculars over here like this. That is basically the normals. So I can just show the normals over here like this. And I can start showing the angles of incidence also. This will be the angle of incidence, even this will be the angle of incidence. Then this would be the angle of refraction, even this would be the angle of refraction. So that is how the diagram will look like. Okay, after some time, the incident wavefront has turned into a refracted wavefront and it has turned by some angle. Now, one thing is clear. In the time, let's say tau, the incident wavefront AC's point, this incident wavefront AC's point labeled C reaches B, it reaches, this C reaches B, I would say the secondary wavefront generated at point A reaches, this point A's wavefront would have just reached point labeled D. So by the time this reaches here, this wavefront which was generated before will reach over here. This is seen in the simulation over here. So this is still here. This has now just started behaving like a secondary source. It will generate secondary wave. It will generate, and finally you will see this point has reached here. This has reached over here. That is what I am trying to explain over here. Okay. Now, what you can say is basically this particular distance labeled C to B is nothing but speed of light into the time taken, and similarly the distance A to D is speed of light into the time taken. Time taken is the same from here to here or here, but the speeds are obviously different. Okay, now you look at this triangle and look at this triangle. Well, if this angle is I, or rather this angle is I, guys, think about it. This angle will be 90 minus I, and this angle will be I again. Similarly, over here, if this angle is R, this angle will be 90 minus R, and this angle will be R again. Okay. So now think and tell me what will be sine of angle I. Sine of angle I in this right angle triangle is opposite side, which is nothing but CB, divided by hypotenuse, which is nothing but AB. Similarly, if you just try to find what is sine of R, opposite in this triangle, opposite side is nothing but AD upon the hypotenuse which is basically AB. So how about dividing both, because I can see AB is common. So if I write sine of I and divide it with sine of R, clearly what I get is AD over here and I get CB over here. That's it, equal to. Is that right? Because AB and AB will get cancelled. So sine I by sine R will be this by this by this by this. AB and AB obviously has got cancelled. AB and AB has just got cancelled. But wait a minute, what is CB? CB is nothing but V1 tau. What is AD? AD is nothing but V2 tau. Tau also gets cancelled. So what am I getting? What am I exactly getting? Sine of I is equal to sine of I by sine of R is V1 by V2. This particular ratio is nothing but a constant. This is called as the refractive index, and this will be a constant because the speed of lights are the same in a particular medium. So if you take a medium, V1 will always be the same. V2, if you take some other medium, V2 will always remain the same. So this ratio is constant. So that is called refractive index, and this is nothing but your Snell's law. So that is how Snell's law can be proven. That is how Snell's law can be proven. Got it? Tau is nothing but the time. In the time tau, time is taken. I can take T, T1, T0, T0, capital T, tau, whatever, some symbol for time. 5 seconds, 3 seconds, 100 seconds, 1 minute, 2 hours, 0.1 millisecond, anything. Cool. Now the same thing analysis is also done for dense to rare over here. It's instead of bending towards, it will bend away. It will speed up. So you can see it will bend away. That is what has been shown in the next diagram. That is not so important, but you have seen it. Now over here, the next part is about reflections explanation. How you can explain the law of reflection using Huygens principle. Again, they use some geometry and they have explained how this is the law of reflection. Once we have the laws of reflection and refraction, everything else can be understood. We'll come to that. Okay, but before it, let's see how the reflection can be explained in a similar way. It is very simple, not that difficult. Again, you take a mirror. Again, you show this is basically your incident wavefront. These incident wavefronts are propagating slowly. They will keep going like this. They will keep going like this. And they will fall onto this particular mirror. They will fall onto this particular mirror and they will get reflected. So how will that exact reflection occur? Let's have a look. So as time progresses, eventually you will see one side of the wavefront will reach the mirror, which is the reflector. Meanwhile, the other part of that wavefront would not yet have reached the mirror. So it is still in air. Now the point which reaches this particular reflector, which is nothing but a mirror, it will start generating secondary wave. But remember, this time when it behaves like a secondary source, when it behaves like a secondary source, it won't generate a secondary wave here, because it is a reflector. It will reflect, so it will start generating a secondary wave here, and that too at the same speed. So it will generate a secondary wave exactly at the same speed with which these waves were traveling. Now, okay, fine, it is now going to behave like a secondary source. It has now going to start generating secondary wave. So after some time it generates this secondary wave. Meanwhile, what would have happened, this particular wavefront would have gone little bit ahead over here, and this point will now behave like a secondary source. The light has gone slightly more ahead like this. In the next instant, you will see that same light will go even more ahead, and then this point will behave like the secondary source. Meanwhile, this secondary source would have generated the secondary wave. This secondary wave would have grown in size. After some more time, you will see that maybe eventually this entire incident wave will finally reach over here, and then this will behave like the secondary source. Meanwhile, this would have already generated a secondary wave. This secondary wave would have already grown in size. This secondary wave would have further grown in size. So that is how the secondary waves start getting generated. So in general, if you see what would have happened, in the time this wavefront eventually reaches over here and then behaves like a secondary source, the initial secondary source, which was starting to reflect the light, would have grown much larger in size. The other secondary sources, not so much in size, but will look probably something like this. Over here. These are the reflected wavefronts. These are the reflected secondary wavefronts. What do you do to such reflected secondary wavefronts? Obviously, you have to draw a common tangent to all of them. To figure out the reflected wavefront. So this then becomes your reflected wavefront. Reflected wavefront. And this particular reflected wavefront then obviously will go like this. So the incident light was reflected. So the incident light was basically reflected. Got it, my dear warriors? Yep. Yes. Thank you so much, guys, for reminding me to hydrate. So this is how reflection occurs. All right. Now, based on this, you can find out how the wavefronts will look like for any kind of object. Like, for example, they have given over here for a prism, for a convex lens, for a concave mirror. So these kind of questions have come in the exams as objective type. How to figure this out is not very difficult. See, whenever light will travel through a medium, it will become slower. So think as if you are taking the wavefront as a pen and the lens, prism, whatever as a rough surface. So imagine this particular pen was traveling, it encounters a rough surface. So the rough part will slow down the pen, and this part is rough but only for smaller duration. This is rough for a longer time. So the pen will slow down over here for a longer time. This will be also slowed down but for not so long. So that's why the pen will bend like this. So think of the wavefront also to be exactly like the pen and the medium to be like a rough patch. Here also, just imagine the rays which will go here, they will be slowed down for a smaller time. Rays which will go here slowed down for a smaller time, but here they will be slowed down for a longer time. So here they are slowed but for less time, so they will come out and go fast. Here they are slowed but less time and they will come out and again go fast. Here, because they are stuck for a longer time, by the time they come out, they are much behind these two people. So that's why you will see the wavefront is bent like this. That's why you will see the wavefront is bent like this. Is this clear? Understood how to solve these kind of questions? Similarly, over here, if you have a parallel beam of light which is incident on a concave mirror, just imagine when the light rays will fall over here, this will behave like the secondary source, this will behave like the secondary source, but this will behave like a secondary source later on, because these rays will hit first. Which rays will hit first? The rays on this part and this part. This part will hit first, whereas this ray will hit the mirror after some time because it is much ahead of these 2 points. So they will start generating waves first. This will generate, but after some time. Meanwhile, they would have grown in size. Alright, they would have grown in size over here. So if you draw a common tangent, it will look something like this. So that means the rays will finally meet somewhere at the focus. So this plane wavefront has been turned into a curved wavefront. So that's how the wavefront behavior is. Cool, clear, very good, Sukanya. Awesome. Che Sukwasi, you completed 2 chapters of physics. You can't complete, realistically speaking, or the entire physics in 1 month. 12th standard, at least the high weightage, yes, and that is a good plan. Don't try to push yourself just to complete physics, because then you will lose out in chemistry and biology. Keep a realistic plan. By January end or February, you will complete the syllabus. That is also decent enough. Trust me. You will get good time for revision. Because if you just try to cover the syllabus, you will feel exhausted. You will forget everything. You will not have time for revision. You will not do it in depth. You have time, and I have given a plan on how you can complete the syllabus by February, March, and still do 2 revisions. Just check out my old video. Okay, so let's have a look at one of the examples when light is incident on a surface which has 2 media. The reflected and the refracted light both have the same frequency. Why? See, it's very simple. Why, when light which is falling on a surface, why when it gets reflected or refracted, the frequency never changes? Because frequency is the rate at which the disturbance occurs. It has got nothing to do with the medium's characteristics, whether it is a reflector, whether it is a lens, whether it is a prism. If the disturbance reaches here, and then after some time the disturbance reaches here, after some time the disturbance reaches here, that defines the frequency of the wave. How frequent are the crests moving? How frequent are the troughs moving? So once I know at, okay, every 5 seconds a crest is reaching, that's it. After 5 seconds, I know a crest will be generated. Yeah, that crest might move slow, fast, depending on whether the medium is dense or rare. But that cannot be, that cannot deny the fact that the crest will still be generated after every 5 seconds. Just because it is moving slow does not mean the frequency will change. No. The frequency will remain unaffected. Okay, so it's the rate at which the disturbance is being created and how it moves. When light goes from rare to dense, the speed decreases. Does the reduction in speed imply a reduction in the energy carried by the wave? What do you think? Do you think energy also goes away because it has now become slow? Obviously not. Energy can't be destroyed or created. All such questions, wherever energy is it conserved, always the answer is yes, energy is conserved. So is energy being lost somewhere and is it disappearing somewhere? Always the answers are no, the energy is not, you can't magically disappear that energy. So it definitely is not going anywhere. In fact, the amplitude of the wave might change to make sure that the energy is still preserved. Yeah, the speed might be slow, but maybe the amplitude becomes large. maybe then it compensates for it. In the wave nature of light, intensity of the light is determined by the square of the amplitude. What determines the intensity of light in the photon picture of light? Well, if you remember, when you take wave nature, intensity is always proportional to the amplitude square. This is true for a wave. But when you take a photon, remember the intensity, I have just discussed this in yesterday's photon, your day before yesterday's photon photoelectric effect class. There is a formula given by N by T HF by A. It depends on the number of photons which are incident per unit time and not on the amplitude. Because how many photons of light are going decides how intense that beam of light is in the particle nature of light. Yep, very good. Cool, great. So now let's discuss something called as coherent and incoherent sources, and then let's come to the main part, which is the interference of light and Young's double slit experiment. Now what is this coherent and incoherent? You might have been in an assembly prayer, or maybe some class songs have to be sung, you have to sing in a chorus, or you are in a part of a group song or something like that. 100% you would have played some kind of role in your school or in your college. Have you? Are you good at singing in chorus or in a group? Maybe not one or two people, maybe at least some 5-10 people, or the entire class has to sing some prayer or something. Imagine that prayer has some nice notes, or it has some crazy, I would say tunes. One person is singing in one way. One person is singing ah, one person is singing ba, one person is singing ma. So it will not sound very right. But if they are in sync, it sounds so melodious, or it sounds better. So coherence means you are in sync and you are having a kind of relationship. And it is not necessary everybody has to say the same thing. Like, okay, when the drummer is hitting a beat, then this lyrics has to be sung, or maybe the keyboard person has to play a certain tune. It has to be in a rhythm. There has to be a relation. When I'm giving the beats, with the beats, you have to make sure your tempo of the song is, or the pace of the song is, and accordingly you are strumming the guitar, or you are playing the keyboard along with the rhythm. So if you are in the rhythm, you are in the sync, such a system of sources, such sources are said to be coherent in nature. Coherence means you are in rhythm, you are in sync, you are maintaining a phase, you are keeping that situation intact. Whatever situation was there before, you are making sure that situation is intact. So whenever the drummer hits, after a second, you are always saying a particular lyric or a tune. Again, when he hits, again you are making that pitch high. Again, when another beat comes, then the tune is something different. So you are maintaining a phase or a situation. Incoherence means you are just random. The drummer is hitting on his own, the keyboard person is doing something on his own. It's looking like one ridiculous performance, as if you are going to get tomatoes thrown on your face. Okay, so everybody is doing their own stuff. The drummer is like, no, I will be very fast. The singer is like, no, I will be very slow. I will sing as if I am very, very sad. The pianist is as if he feels like he's opening the track of some Christopher Nolan movie. The keyboard guy or the guitarist is saying that, no, I feel like I'm in a rock band, and he's playing a rock song. So this kind of thing, there is no sync, is called as incoherence. Now, because incoherence means that there is no sync, there is no rhythm, there is no relationship, there is no point discussing such an incoherence behavior, because it is random. How do I talk about something which is random in nature? I don't know what they are going to do. So sometimes the light is bright, sometimes the light is faint, sometimes the light is green, sometimes the light is blue. I don't know what they are going to do together. But I know, okay, this is blue light, this is also blue light, this is the amplitude, this is amplitude, okay, they are going to be together here, and every time this is going to happen. then I can comment, I can formulate, I can discuss about it. So that is the reason why we discuss coherent sources and we do not study incoherent sources. Is this clear, my dear warriors? Yes, sir, I sing a prayer. Swati, very good. So I hope you are a coherent singer at the prayer, because I was an incoherent singer. So I was always that person in the class along with a small group of kids who used to make sure that our class never wins in any kind of singing competitions. We will always make sure that we are out of tune. Yes, it will feel like there are 2-3 donkeys in the class who are trying to make it out of tune. Yep. So the entire field of interference is based on the superposition principle at a particular point of the medium. The resultant displacement produced by number of waves is the vector displacement of these waves. Consider two needles moving periodically up and down. They produce water waves. Okay. Then, okay, over here they talk about coherence. The phase difference between them, if it is not changing, then they are said to be coherent in nature. That figure shows coherent sources, and then they basically do some kind of derivation. Examples of coherent. Which are coherent? Example, this one. Yes, these both waves are coherent in nature. These both are coherent in nature. Okay, so definitely these two are coherent in nature. Then look at this. Sorry. Even these both are coherent in nature. They are not identical, but they are coherent, meaning, see, this is going up, down, down, up, down, down, up, down, down, up. Yes, they are again coherent in nature. Even this is coherent. Just look at this. Even this is coherent. When this is a trough, this is crest, crest, trough, trough, crest, trough, crest, crest, trough, crest, trough, crest, trough, crest, trough, opposite. So it is maintaining the phase difference. So basically the phase difference is nothing but a constant. All these are coherent. Which are not coherent, let me give you those examples also. This, yes, definitely not coherent. Or something and all, this is, these two have no relation only between them. There is nothing that you can relate. So they are incoherent sources. Okay. Now we are going to study the interference of such coherent waves. So for that, let's come back over here. Remember, a speaker can generate wavefronts. Even, by the way, light can generate wavefronts. So this is the wavefronts of light, beautifully looking. You can see how light is being generated. This was green color light. Now if I use violet color light, see the violet light is looking like this. I don't know whether you can see it. If I use red color light, you can see it like this over here. Look at how red color light, the distance between the wavefronts is slightly larger because light has a larger wavelength. Yep. Whereas if you look at violet color, you can see they are slightly closely spaced because the wavelength of violet is lesser as compared to yellow or basically red. As you can see, yellow is slightly larger, and then when you make it red, it is the largest among the visible spectrum. It is the largest among the visible spectrum. Now I will create two such wavefronts together. Let's create two such wavefronts together, and for that we'll create interference. First, let's study with water, then we can go to sound and even light. It is a general phenomena. This theory is not just limited to light. It is, although a part of wave optics, you can use it in sound or even water or anything else. So let's start generating wavefronts over here. You can see drops of water are falling on the pond over here. Wavefronts are being generated. Now if I turn this off, it's gone. Okay. If I turn this on, it will generate its own wavefronts from here. So this is another source. This is the first source. Now what if I turn on both the sources together? Then what do you see? They are in sync, they are synchronous, they are in phase, or basically phase difference is constant, so they are coherent sources, and you can see some kind of interference being happening. The crests are meeting, the troughs are meeting, somewhere there is constructive interference, somewhere there is destructive interference, and so on and so forth. So wherever constructive interference is there, these water drops, those ripples which will be formed, those tides will be high, and wherever there is destructive interference, that means the waves cancel out each other, there will be no variations in the tides. The ripples will cancel out each other. Probably somewhere here you can see there is no variation, only much somewhere here in this line, or even in this line there is not much variation, but here I can see a lot of variations. It's going down and up, black is down, blue is up, so a lot of variations are there. We can try it out with waves also for sound. This is a speaker generating a wave. This is another speaker also generating another wave. And we can see how at some places constructive interference is there. That means if you stand over there, both the speakers will have a constructive effect. Means you will hear a loud sound and you will hear a very good intensity of the sound. But there are some places the waves are cancelling out each other, so that sound is getting interfered destructively, means you will not hear any sound. And that is actually very funny to think of. There are two speakers in front of you, yet when you are standing in front of them, you are not able to hear anything. So this is actually a technology which is used in many of the cars, modern cars, like the high-end cars, like Rolls-Royce or maybe the Mercedes Maybach and all of that, where they ensure that if the backseat passenger is talking on a business call to his client or his customer or to his business colleague, the driver won't be able to hear anything, and that is being taken care of by noise cancelling and interference of sound. So they have multiple speakers in the car, and they ensure that if the back seat passenger is on the call, maybe he's a very important person, politician, who knows, maybe some military discussion is going on, the driver won't be able to overhear what is happening because he's in the destructive zone of interference. We can separate them out or we can bring them close, and you can see how the interference patterns will change. Look at it. Now they are very, very close. Now the interference pattern is looking way, way different. I can see these lines, okay, making some angle. If I change this, you can see it is way, way different now. Observe how things change drastically. Okay, so the interference patterns change as you change the distance between the sources, and not just that, it also depends on the frequency. If I increase the frequency also, you can see how the interference patterns will change. Yes, the interference pattern has changed. I have increased the frequency. If I reduce the frequency, again the interference pattern which is obtained will again change, obviously. We can also see it with particles, how the particles behave. This is the particles of air, how sound travels in reality. So you can see there are some particles which are actually moving back and forth a lot, but you can see this zone or even this zone over here, the particles are not moving much, so very less sound is there, whereas at some places the sound is really, really high. Same thing applicable even for light. So let's say we use both these lights, and both these light sources are switched on together, they are coherent necessarily. Then you can see some places there will be a lot of brightness, some places there will be absolute darkness. Yes, some places it will be bright, some places it will be absolutely dark because of destructive interference. I can change the separation. Again, I will see the interference patterns will change, as you can notice. I can also change the wavelength or the frequency of the light. Automatically, again, the nature of the interference will definitely change. The best part is you can observe this interference on a screen through a naked eye by placing a screen in the front. Wherever constructive interference is happening, you will see bright regions over there. These are bright fringes, bright bands, and wherever destructive interference is happening, you will see dark fringes over here. They are the dark bands or the dark fringes. And you can see changing the separation obviously changes the manner in which the bright and the dark fringes are created, how far they are separated. Now you can see one big bright fringe, so the other bright fringe is way out of the screen. Maybe I'll have to change the distance between the sources, maybe then I will be able to see it. Yeah, so how much fringes you can see, what's the width, what's the distance between them, all that depends on the distance between the sources and even the light's frequency or the wavelength, as you can see over here. See, I've changed the wavelength, I've changed it to blue color now. You can see now the fringes are very, very different in nature. The fringes widths are different, the distance between the fringes are also different. You can see the intensity graph over here. This is minimal intensity, that means it's a dark fringe. Maximum intensity means it's a bright fringe. Dark, bright, dark, bright. You can see it for different colors also. Let's say yellow color also, we can try it out. I can choose some different separation. Observe this, how it behaves. There is a screen which is placed in front. You can see the plot, the intensity over here. Dark, bright, dark, low intensity, bright, high intensity. Dark, low intensity, bright is high intensity. So this is how the intensity graph will look like. Now basically this setup what you are seeing with light is called as a Young's double slit apparatus or Young's double slit experiment, where they use two slits and there is a light source. The light falling from that source enters through these two slits, and these two slits behave like two coherent sources, and their light eventually through a dark room falls on a screen and you see a pattern which is a fringe pattern, bright and a dark fringe pattern, alternate bright and dark bands. From this you can do calculations of whatever you want, either the wavelength, the distance, whatever you want. And this experimental setup is called as a Young's double slit experimental setup, YDSE. So after the name of the scientist, physicist Young, there are two slits. Instead of two light sources, there are two slits which are made, small holes. There is a bulb here. The light falls on this, but only a small part enters from here and here, and that light finally reaches both reaches the screen after interference, producing this fringe pattern. Are you able to visualize this? Yes or no? Are you able to understand whatever I explained till now? Let me know quickly in the chat box. Did you understand what interference is? What is a dark fringe? What is bright fringe? Yeah, we'll do the calculation part now. Hold on. But did you understand all these things is the main question. Yes, everyone? How this works? If you just turn on one, then there is no interference pattern at all. Look at this. I've turned this off. Only one light source is there. Then you will see the entire screen will get illuminated. There is no more interference. No more interference. Very good, Sukanya. Evening start. Awesomeness. Very good, Madhumati. Crystal clear. Mardai. Very good. Awesome. Okay. So here, where did they go? Yeah. After this, they have done some derivations over here. All right. And then they have given some formulas over here and then over here. So we'll see what these formulas and these derivations are in a very simple manner. First of all, when you talk about constructive interference, although we have discussed this for waves and superposition, I'm just repeating this aspect again over here. If you have a wave like this, In such a case, if you add them together, by the way, here delta x, the path difference is 0, the phase difference is also 0, or let's say like this. This is exactly having a path difference of lambda, which means the phase difference is 2 pi, and you add both these waves, or this path difference is 2 lambda, the phase difference is 4 pi radian. All these cases, observe carefully, the trough meets the trough, the crest meets the crest, the crest meets the crest, the trough meets the trough, the trough meets the trough, the crest will meet the crest. All these are examples of constructive interference. Path difference can be 0, lambda, 2 lambda, in fact even 3 lambda. All of them will give a big amplitude. It will give them a big amplitude, yes, of interference. It will give a big amplitude, and in general I can then say that my path difference can be n times of lambda, my phase difference can be even multiples of pi, meaning over here this can be lambda, 2 lambda, 3 lambda, and so on and so forth. This can be 0, this can be 2 pi, this can be 4 pi, 6 pi, like that. And the net amplitude in such cases, is just the first amplitude plus the next amplitude. Whereas if you talk about the intensity, that will be also maximum, and we have derived this we have seen this in this particular lecture. If you have missed this class, I'll just show it to you over here. Superposition of waves, where did it go? Interference, standing waves and beats. Just check out this lecture. You will find that theory where I have discussed about interference. Okay, right over here. You will see in the beginning, yes, in phase, out of phase. We have seen it graphically. I have shown you how it works. All these things has been discussed right over here. So just check that out. So the intensity is maximum, and it will be root of the first wave's intensity plus root of the second wave's intensity whole square. Yeah, that is what the intensity is going to be. And constructive interference happens when the waves are basically in phase. They are said to be in the phase. That's when you will get, yeah, maximum intensity, constructive interference, maximum amplitude. This amplitude is not just any amplitude. This is the maximum amplitude that you can get of that waves which are interfering. Are you reminded of it, everyone? We'll not be doing modern physics NCERT line by line because like I said, modern physics is better learnt through normal NEET theory, not through NCERT line by line. So it's better to do it that way. And already in NEET Express Station 0, it was done in that particular way. Now, similarly, when you talk about destructive interference, when you talk about destructive interference, that means the waves will be out of phase. So things like this will happen. These two are added. Over here, you can see the path difference is lambda by 2. Basically the phase difference is pi radian, or yeah. So you can see this is 3 lambda by 2, and here the phase difference, if you do the calculation, it will be 3 pi radian, so on and so forth. You can add these two waves. What you will see is a smaller wave. You will see a smaller wave because it is destructively being interfered. Okay, so in such a case, the phase differences allowed and the path differences will be, the path difference can be lambda by 2, 3 lambda by 2, basically it is odd times lambda by 2. Now lambda by 2 is 0.5, 3 by 2 is 1.5, so it will be basically like 0.5 lambda, 1.5 lambda, 2.5 lambda, so on and so forth. But if it is integral lambda, 1 lambda, 2 lambda, 3 lambda, then it is constructive interference. And you can see over here, the crest meets with the trough meets with the crest. The trough meets with the crest. Okay, the next crest will definitely be meeting the trough over here, like this. So it is definitely a destructive interference. Whereas if you talk about the phase difference which you will get over here, you can see it is pi, 3 pi. Pi is basically out of phase, opposite. So basically odd multiples of pi. So basically it will be nothing but pi, 3 pi, 5 pi, and so on and so forth, 7 pi and all that. The amplitude will be the least that you can get. So whichever is bigger minus whichever is smaller. So mod of A1 minus A2 will be the amplitude. If you ask me the intensity, that intensity will also be minimum. It will be root of I1 minus root of I2 whole square. Root of I1 minus root of I2 the whole square. Is this clear, everyone? Okay, perfect. Now just imagine, say for example, if the two coherent sources causing interference are identical. If they are identical, that means A1 is equal to A2 is equal to A, I1 is equal to I2 is equal to, let's say, I will call it I, then the maximum amplitude that you will get is nothing but A plus A, which is 2A, and the maximum intensity that you will get is root I plus root I whole square, which is 2 root I the whole square, which is basically 4 times of I. This is the maximum that you will get. This is for your constructive or for maxima, or the maxima that you can talk about, where everything is maximum, or where everything is going to be bright and loud. If it is a sound, it will be loud. If it is light, everything is bright. This is what the intensity will be. It will be 4 times of I. The amplitude will be double of the each wave's amplitude. That is for the constructive part. But if you talk about the destructive part, the amplitude will be the least. In fact, it will be A minus A, both are the same, it will be 0. This is called as a perfect destructive interference. It is a perfect destructive interference because it is cancelling out. The intensity will be minimum. In fact, that will be root of I minus root of I the whole square, it will be 0. It is then perfect destructive, nothing is there. And this is your destructive, or I would then call it as the minima part of it, or this will be the dark region of the interference because of those two sources. This will be the dark region because of these two particular sources. We also know that when this thing will happen, in general, if you want to find the intensity, in general, if you want to find the intensity or the amplitude will be given by root of A1 square, this is the resultant amplitude, A square plus 2AA cos del phi in general. You can see A can be taken out common and I will be left with 1 plus 1 plus 2 cos del phi. This can be further written down as nothing but I can just take over here root 2 1 plus cos del phi. That is what I can write it down as. If you want, you can write 1 plus cos del phi, 1 plus cos del phi as 2 times cos square delta phi by 2. This is a trigonometric formula. If you know this thing, cos 2 theta is equal to 2 cos square theta minus 1. Take that 1 over here. So cos 2 theta plus 1 is 2 cos square theta. So just imagine, if I write cos phi over here plus 1, it will become 2 cos square phi by 2. So 1 plus cos phi will be 2 cos square phi by 2. So that is where this particular formula comes from. Yes, modern physics of 2024, you can use it for studying. Why not? You can use my Super 6 theories definitely even in 2025. It's not like it is invalid. I'm not like Huygens or some other scientists. Suddenly in 1 year the theory is invalid. You can use it. Okay. So if you want, you can write this 2 into 2 as 4. Root of 4 is 2. So it will become 2a, and root of cos square is just cos del phi by 2. So that is the resultant amplitude. Similarly, you can also find the resultant intensity, not a big deal. So the resultant intensity will be I1 plus I2 plus 2 root I1 I2 cos del phi, which is the phase difference. So I is basically common, and what I'm left with is 1 plus 1 plus 2 cos del phi. Again, the same theory is applicable. It will just become I into basically 2 common and 1 plus cos del phi. 1 plus cos del phi, we just saw what it is. It is nothing but 2 cos square del phi by 2. 2 2s are 4, so it will become 4i cos square del phi divided by 2. So that is your resultant intensity in general when the two sources are identical in nature. This is very, very important. If they are identical, if they are not identical, then obviously they will not cancel out perfectly. This formula will not be applicable. This and this will be different. This I and this I will be different, and all of that. Is that okay? Everyone understood? This is only for two identical coherent sources. Two identical coherent sources, what the amplitude and the intensity in resultant will look like. So I'll just block this off, and this is the most important word: two identical coherent sources. This also obviously are very, very important. As you can see, the maximum intensity will be 4i, whereas if you talk about the minimum intensity over here, that will be just 0. It will just cancel in the case of destructive interference. These formulas I have given you even in the previous lecture. This is just more like a recap or revision of this. Okay, cool, very good. Now what they do is, say for example, I have two sources over here, S1 and S2. There is a space around it and I want to know where constructive happens, where destructive happens. So that is why I will choose some random point, let's say over here. I don't know whether it is going to be constructive, destructive, or neither of them. So I will think of it like this. Okay, the rays from source 1 will reach point P earlier. In this case, the rays from source 2 will reach it slightly later on. Let me join the two sources by some distance. Let's say over here, I will call it as D. Okay, I'm just going to call the distance between the two sources as D. And the location of the point, which is right over here, I will label it as R. And I will just show a perpendicular to S1 and S2, something like this. I will also mark an angular position of that point. I will call it theta. So what have I done over here? Just observe. S1 and S2 are two coherent sources separated by d distance, d, and you have taken a random point P at distance R, which is much larger than our D. If it is very small, it becomes difficult to analyze. So usually those distances, this point is very far from the sources, or you can think like this: the sources are here, this point is here. So this R is very large as compared to the distance between the sources. Okay, and has angular position given by theta. Angular position is given by theta. What I want to know, if both these sources generate waves, they won't reach the point P simultaneously. Obviously, this wave will reach first, this wave will reach a little bit later. If point P was here, then this will reach late, this will reach earlier. So there is a delay, there is a path difference which is created. So that path difference will help me understand constructive, destructive, and so much more. So if I want, what is the path difference in general at that particular point? So I will write over here the path difference by the time the waves reach here, that delta x will be this path length minus this path length. So it will be S2p minus S1p. It will be nothing but S2p minus S1p. Everyone fine till this point? S2p minus S1p. Now, this is the very interesting part. Observe this. If this S2p distance, and this S1p distance, subtraction is delta x. If I want a constructive interference, then I will make sure it is n lambda for constructive, for bright regions. And if I want destructive interference, I will just ensure this delta x is odd times lambda by 2 for dark regions. That means my point P is somewhere and I have taken two fixed points, and the difference of the distances, if it is, let's say, 5 lambda, then I know it is a constructive interference. If the difference of the distances is 7.5 lambda, because odd by 2 will be like 0.5, 0.5, 1.5, 2.5, 3.5, 7.5, 2.5, whatever.